Good evening. Um, Today is June 30th, 2026, and International Asteroid Day. Welcome. This is a presentation of the Fort Worth Astronomical Society. I'm Chris Mudnitsky. Um, let's see. In December of 2016, the UN decided to adopt a resolution declaring the 30th of June to be International Asteroid Day to observe every year at the international level the anniversary of the Tunguska impact event over Siberia in the Russian Federation on June 30th, 1908, and to raise public awareness about the asteroid impact hazard. So, International Asteroid Day also aims to inform the public about the crisis communications actions to be taken at the global level in case of a credible um, near Earth object threat. And today we're going to talk about asteroids, what they are, finding the hazardous ones, and we're going to get into some mitigation uh, ideas and then into meteors and meteorites. So let's go ahead and get started. All right, there we go. Okay, so we have a picture of an asteroid, we have a picture of a meteorite on the ground. So let's go on. If you have any questions, if you have any comments, concerns, you can go ahead and put them in the YouTube chat and I will be reading them and I'll be trying to respond to them as quickly as I can. So, asteroids and meteoroids. So the quick overview, asteroids are objects in the solar system, generally over a meter in diameter. And meteoroids are things less than a meteor, 1 meter in diameter. This definition will also apply to anything outside the solar system, um, but so far our instruments aren't sensitive enough to detect anything smaller than a planet um, for now. So, meteor. A meteor is the visible path of a meteoroid that enters Earth's or another body's atmosphere. A meteorite is the meteoroid that impacts onto the ground. And the word comes from the ancient Greek meteoros, meaning high up in the air. So the ancient Greeks knew that meteors were something very, very high. They didn't know how high, but they knew it wasn't close. They didn't hear anything from them. It was very, very far away, and they never really found anything. Don't know if they ever went looking, but I don't think we have any records of the Greeks finding very many meteorites from a fall. Asteroids. These are large objects ranging from a meter to more than 500 kilometers across. The big ones are at least somewhat round and they're differentiated like planets, which means that they have a core, a mantle, and a crust. The smaller ones can be solid or they can be rubble piles, just a bunch of rocks and dust that's in a big conglomeration because of gravity. Most of the meteorites that we have come from impacts on asteroids. Excuse me. So something hits the asteroid, knocks off some chunks. They fly around for a very long time and eventually land on Earth or another planet. All right, types of asteroids. The C type, the chondrite asteroids, we think they're the most common ones. They're made mostly of silicates and clays, and they're some of the oldest undisturbed objects in the solar system. S types are stony. They're made of, of silicates and a little bit of nickel iron. Then we have the iron, the metallics, M types. So they're just big hunks of nickel iron. Some of them are the remains of larger differentiated asteroids, the cores in the center, and others were partially melted during their formation. So the iron, the nickel iron went down to the center and then eventually solidified. So the very first asteroid discovered was Ceres. It's the biggest one in the asteroid belt, and that was in 1801. Took another 48 years to find the first 10, so the next 9. It's a long period of time. With better instruments, we found 90 more in the next 19 years. And then as telescopes got better and better and better, we started using photography. We found 1,000 by 1921, 10,000 by 1981. And then with the dawn of digital sensors, computerized automated surveys, a number of asteroids grew very, very, very quickly. As of right now, we found more than 1.3 million asteroids. More than 42,000 of them crossing Earth's orbit. And we've named about 23,000 of them right now. We have a question from the chat. What are the chances of a meteor hitting a satellite or the International Space Station? They've been hit. They have been hit by objects. We don't know necessarily if they were just orbital debris or if they were actual meteors, meteoroids coming from the rest of the solar system. But there have been impacts. Uh, there was an impact on the space shuttle, but they think it was like a paint chip onto one of the windows. Um, the James Webb Space Telescope has Whipple shields, uh, partially to block energy from the sun, but also a way to slow down impacting meteoroids. Um, Whether or not any have hit it so far, I personally don't know. I haven't heard of anything, but that's something that would be interesting to find out. And then there have been some satellites that have been suspected of breaking down and stopped functioning because of impacts, but we're not sure because no one sent up a rescue mission for a satellite that just went offline. Um, they just kind of die, and that's it. We pretty much leave them up there. But yes, it is possible that a meteoroid can hit the International Space Station or other satellites. Let's see if this works. There we go. So this video is a time lapse of asteroid discoveries from 1980 to 2020. The bright white dots are the discoveries, and then they fade into the darker red known asteroids. Um, let's see. We can see as days pass, the asteroids are being found. At this time, it's professional astronomers using larger telescopes of the 1 meter class and higher, using film cameras to take the images. You take one image on a clear night, and then the next night you take the same and another image of the same section of the sky, and then you compare the two. If you see any of the stars move, you take a note, and then you image again the next available night to see if it moves again. And you keep imaging until you figure out the position. If you have 3 positions, you have enough data to calculate an orbit. So amateur astronomers are also finding asteroids just through their own film photos or visual observations. And comparing the stars in the eyepiece with a star chart and finding differences, it's a challenge even for seasoned visual astronomers. So every once in a while, you see a burst of activity. So a little flurry of asteroid discoveries. These are asteroid surveys. They were done as research projects with weeks of observations trying to find new asteroids. And about the mid 90s, we start seeing a speed up of the asteroid discoveries for one simple reason: computerization. Automated computerized telescope mounts started to be developed at cost points that were reachable for smaller observatories and universities, and with them, the very first CCD cameras. So by the start of the 2000s, we're going to see some improvements in technology with costs dropping to the point that amateur astronomers were able to get involved as well. Um, so right now we're still in the mid 90s, and we can see some of these automated surveys where it looks like there's a spike going out because they're imaging one part of the sky and they're finding a lot of asteroids in that one section, but at different distances from the Earth. So we keep on going. So new big camera chips in the early 2000s. They were expensive, but the early adopters, like large research observatories, started to use them for surveys. And the older chips prices went down, so amateurs were able to access better equipment. And we see this continuing today. Equipment and software in the hands of the average astronomer today can produce images as good or better than that of professionals 30 years ago, with shorter exposures and a lot less effort. If you've seen the new smart telescopes, you'll know what I mean. It takes very little. You just put them out there, turn them on, you can start imaging. So by the middle of the 2000s, we start seeing the start of the automated continuous surveys like now. Computers are starting to compare images taken day to day and sending the hits to astronomers to evaluate. And in about 2010, we see something a little bit different. Instead of asteroids being detected just from the Earth-based observations, we have satellites like the Canadian Near-Earth Object Surveillance Satellite. So coming up to that. So with a small telescope and CCD imaging cameras, these are able to look for asteroids 24 hours a day with continuous observation. It's what we're seeing now. Just getting into that. 2000. There we go. So we also start to see the Trojan and the Greek asteroid camps out at Lagrange 4 and 5 near Jupiter. The Greeks lead at L4, the Trojans follow at L5, and at L3 on the opposite side of Jupiter from the Sun, opposite side of the Sun from Jupiter, we've got the Hilda group of asteroids named after 153 Hilda. You can start seeing some of these now, where we have one group here, and there's Jupiter. So here are the Greeks. Here's Jupiter. And we have the Trojans following at L5 in this region here, right there. And then the Hilda group opposite there. So as we're starting to close in on the end of the data set, we can see the automated surveys and a lot more of these near Earth asteroids that we're finding here. I don't have the most recent data yet, but we are over well over 1.3 million asteroids right now that were discovered just from 10,000 in 1980. So big difference. And it's all because of automation. So neat stuff. Yep, I don't have any more data after that. Okay, near Earth objects, NEOs. These are asteroids and comets. They're nudged by the gravitational pull of nearby planets into orbits that bring them close to us. Most are going to be rocky asteroids from the asteroid belt, and their orbits are changed by Jupiter. Jupiter's big. Some are comets. They're made of ice and dust, and they come from the outer solar system, but they get slowed down by planet's gravity and stay in the inner solar system, such as, well, again, it's Jupiter's gravity that's doing it. Excuse me. There are a number of comets like that. The one I can think of right now is Enki. NEOs typically pass within about 30 million miles or 48 million kilometers of our planet's orbit. NEOWISE. This is NEOWISE. This is the Near Earth Object Wide Field Infrared Survey Explorer. NEOWISE was a highly successful NASA Space Telescope mission, concluded in 2024. Originally, it was launched in 2009 as WISE to conduct an all-sky infrared survey. It was repurposed in 2013 to hunt for near-Earth asteroids and comets. Its primary objective was to track and categorize near-Earth objects, refine estimates of their sizes and their orbits. The NEOWISE captured over 1.45 million infrared measurements, discovered 215 NEOs, and found 25 different comets. The mission ended because it kind of ran out of fuel. In order to adjust its orbit, it needs fuel, and it was all out. So without that, there's atmospheric drag even on satellites in low Earth orbit. Even the space station, it gets slowed down and periodically needs to be boosted to a higher orbit. So it was decommissioned August 8th, 2024, and it burned up in the atmosphere November 1st, 2024, and it dropped down at Point Nemo, the spaceship's graveyard in the in the South Pacific, Earth's spaceship graveyard. Point Nemo is the furthest point away from inhabited regions or land on the Earth, and it happens to be a point in the middle of the South Pacific. Ships don't go there. People don't go there. Airplanes don't fly over there because there's nothing there. If you were going to have trouble, there's nothing you could really do. And it's very, very far away for anyone to help you. So we like to drop spacecraft there because it's not going to hit any airplanes flying over. It's not going to hit any boats, hopefully. So the data collected by WISE and NEOWISE, the NASA science mission, it's still a vital resource for planetary defense and solar system research. People still access the data and use it. Okay. Hi. My son is here, and okay. He just came in from playing outside. Okay, can you close the door, please? Thank you. Let's see. Astronomers actively monitor over 42,000 known NEOs to protect against potential impacts. Collisions occasionally do happen. We don't have any significant threats to the Earth at this time for the foreseeable future. And to protect against potential impacts, astronomers monitor the sky constantly for possible threats. The IAWN is a worldwide planetary defense collaboration of organizations and individual astronomers who collectively work to detect, monitor, and categorize potentially hazardous asteroids and near Earth objects. So, if an asteroid threat were to be identified, IAWN would act as kind of a centralized hub to gather all the information and then disseminate it to governments, aid with analysis of impact consequences, and with planning of any mitigation strategies and response options. Think of it as a clearinghouse for data. So, the Center for Near Earth Object Studies runs under NASA's Jet Propulsion Lab, like a great many things do, and that supports NASA's Planetary Defense Coordination Office. Um, this is a table just directly from the website. This is public information. Anyone can go ahead and get it. Orbital solutions are calculated by the group, and they're used to predict NEO close approaches to the Earth and produce comprehensive assessments of NEO impact probabilities for the next 100 years. There aren't any at this time. They use supercomputers to continuously update orbital parameters, close approaches, impact risks, and discovery statistics of NEOs, and to keep track of any hypothetical mission plans to possibly human accessible asteroids. So something comes close, if there's like an orbit that it would be fuel efficient to send a mission to, this is who would know about it and who would be able to calculate everything for you. All the data is publicly accessible. You can actually write scripts to access their API, and you can pull down whatever data you want automatically and for whatever use you want. Again, this is a government study. It is free for everybody. CNEOS also hosts the Sentry Impact Monitoring System. It performs long-term analyses of possible future orbits of hazardous asteroids, searching for impact probabilities over the next century. Then the Scout system monitors the Minor Planet Center's web pages of potential asteroid discoveries and computes possible ranges of future motions for these objects have even been confirmed as real discoveries. So the Minor Planets Center, if you discover what you think is an asteroid, that's where you go. Log your discovery, and they'll kind of take it from there. That information on the website will then be pulled down by CNEOS, and they will work on it. So people will be able to track that, see if it is an actual discovery, or did you have something on your sensor? Hopefully not. We usually take care of those when we do image processing. So in the event of a predicted impact, CNEOS works to predict the impact time, location, impact geometry. When, where, and how is it going to come in and how fast? They use hypothetical impact scenarios at the planetary defense conferences and similar exercises at other meetings. So they compute how far a hypothetical asteroid would have to be deflected by a known amount at an earlier time. So the sooner you can deflect, the less energy you need to do it. So like if there's a asteroid that's 5 or 10 years out, you may just need like a small thruster engine attached to it to push it out of the way, or the gravity of a probe. We'll get into that later as well. But if you wait too late, it may be months away, but it may be too late. I mean, we may not have enough energy to push it out if it's that close. So the Torino scale, this is what we use to categorize and communicate impact hazard associations with near-Earth objects, like asteroids and comets. It was adopted by the International Astronomical Union in 1999, and it combines the collision probability and estimated damage potential into a single number. Its primary purpose is to clearly convey the public threat of an incoming space rock over the next century. So, level 0, object has 0 chance of collision, or it's too small and it'll burn up in the atmosphere. It's yellow. Levels 2 to 4, uh, close approaches that require some calculations by astronomers. Level 4 indicates a 1% or greater chance of causing regional devastation. Levels 5 to 7, highly significant close encounters with a critical, uncertain threat of regional or global devastation. Big and much more likely. And red, 8 to 10, certain collisions, impacts that are mathematically certain to occur. Level 8 is localized damage, level 9 is regional damage and devastation. Level 10, it's a global climactic catastrophe capable of ending civilization. So don't want to hit red. Okay, 99942 Apophis. Several years ago, this was a really big deal. Um, and because it was thought it was going to be colliding with the Earth. So it's an oblong rock. It's about 450 meters by 170 meters, or about 1,500 feet by 560 feet. As space rocks go, it's not very large, but it's more than large enough. So its long axis is about as tall as the Empire State Building in New York City. In December of 2004, initial observations indicated a probability of 2.7% that it would hit the Earth on Friday, April 13th, 2029. Later observations eliminated that possibility of an impact on that date, um, but it will pass Earth in 2029 at about a distance of 31,600 kilometers, or about 19,600 miles, um, above the surface. And it's about as close as the geostationary satellites are, which is this ring that you see here. So this was given a level 4 rating on the Torino scale in December 27th of 2004, but it was later lowered to level 1. And then there was a small possibility that during its 2029 encounter, Apophis would pass through it's called a gravitational keyhole. It's like a region of space, is about 800 kilometers across. Um, and that would have set up a future impact on 7 years later, April 13th, 2036. But in August of 2006, the probability that Apophis would pass through the keyhole was determined to be pretty small. So, and then 2 years later, in 2008, they kind of shrunk down the keyhole. So it has to it has to go through a hole about, or a region of space about 1 kilometer wide. So right now, the Torino scale rating is a 0 for Apophis. Asteroid avoidance, or sorry, asteroid impact avoidance. This encompasses all the methods by which near Earth objects on a potential collision course with the Earth could be diverted, preventing destructive impact events. Whoops, that's all right. There we go. An impact by a sufficiently large asteroid or other NEO would cause, well, depending on its impact locations, massive tsunamis or widespread wildfires. Um, and the impact winter, just like a nuclear winter, caused by the sunlight blocking effect of large quantities of pulverized rock dust and debris placed into the stratosphere, just block out the sun, cool down temperatures worldwide. 66 million years ago, as an impact in what is now the Yucatan Peninsula in Mexico by an object about 10 kilometers wide, or 6 miles. And we think that created that impact crater there, Chicxulub, and triggered the Cretaceous Paleogene extinction event that wiped out all of the non-avian dinosaurs. Yes, I use that term specifically because birds are dinosaurs. If dinosaurs were around, we would just call birds feathered dinosaurs. So, um, asteroid impact avoidance. We've been looking at finding the potentially dangerous asteroids now. So, what do we do about stopping the most dangerous ones from hitting us? So far, we have nothing. Um, Nothing ready, at least. We have a lot of ideas, things we can do, but there is actually nothing that is built right now that we could launch it tomorrow. So if we found an asteroid that was going to hit us the next few months, it's very unlikely that we could do anything about it. The asteroid tracking and warning system we have in place buys us time, but we have to have some real strategies about what we're going to do in the future. So what are some options? Well, its strategies kind of fall into two basic sets: fragmentation and delay. Fragmentation concentrates on rendering the impactor harmless by either fragmenting it and scattering the fragments so they miss the Earth, or they're small enough to all burn up in the atmosphere. Delay exploits the fact that both the Earth and the impactor are in orbits. An impact occurs when both reach the same point at the same time, or more correctly, when some point on the Earth's surface intersects with the impactor's orbit when the impactor arrives. Since the Earth is approximately 12,750 kilometers across, or sorry, in diameter, 7,920 miles, um, and it moves at about 30 kilometers a second, or 19 miles a second, in its orbit, it travels a distance of one planetary diameter every 425 seconds, or just over 7 minutes. So that means if you delay or advance the impactor's arrival by that magnitude, a little bit more than 7 minutes, depending on the exact geometry of the impact, it can miss the Earth. So it doesn't take a lot, but only depending on when you actually start. So we don't have to necessarily blow it up. Okay. Um, what matters is that we provide enough kinetic energy to the asteroid to deflect it, and that could be like shooting impactors, like for the DART mission. The double asteroid redirection test, was a controlled experiment. It took place some 11 million kilometers, 7 million miles from the Earth in 2022. It was really neat. We got to see it nearly live on TV from NASA. So it was a refrigerator sized satellite, and it drove straight into a 160-meter wide, 525-foot Dimorphos asteroid at 22,000 kilometers an hour, or 14,000 miles an hour. And it blew itself up in the process. The space rock orbits a much larger object called Didymos, and Didymos is 780 meters across, or 2,550 feet. So one orbit was 11 hours and 55 minutes. When we observed it after the impact, the orbit was changed. It was reduced to 11 hours and 23 minutes, 32 minutes shorter. So we were able to affect this. The first time that we've been able to affect the orbit of an asteroid, even though that asteroid was orbiting around another asteroid. But it was a good test because we could very quickly see that the orbit changed, as opposed to having to wait perhaps several weeks to months to see how much the orbit changed on a um, uh, it's called a free floating asteroid in the asteroid belt. Blowing up an asteroid, that might not be a great thing. So we talked about rubble piles earlier. Some asteroids are just groups of rocks that are just holding together only from gravity. So if you imagine a rubble pile breaking up into pieces, but most of the pieces are still heading our way. Now it's not like a rifle bullet. Now it's a shotgun blast, and that may not be any better. So instead of having a localized impact, now you can have a widespread impact, perhaps across an entire hemisphere. So one idea is to use a nuclear explosive device either above, on, or just below the surface of an asteroid. Where depends on the object itself, how big it is, its composition, a lot of factors. We don't need to get into that today. Um, but it does not require that the entire object has to be vaporized. So, in the case of an inbound threat from like a rubble pile, use a standoff that the detonation height above the surface um, can be used to prevent the entire asteroid from fracturing and blowing apart. We just want to push it away. So, if you set off a nuclear weapon, let me if you initiate a nuclear device, let's use the proper language. If you initiate a nuclear device above an asteroid, um, the energetic neutrons and the X-rays released by detonation don't really penetrate deep into matter. They're converted to heat upon hitting the surface, and they can ablatively vaporize exposed surface parts of the object to a shallow depth, turning the surface material into ejecta. It literally blows off, as in the picture. So basically, you turn one side of the asteroid into a rocket engine. You change the velocity, or and you're nudging the asteroid off to one side. So, following Newton's law, ejectas goes one way, and the object being propelled in the opposite direction. Depending on the energy of the explosive device, the resulting rocket exhaust effect created by the high velocity of the asteroid's vaporized mass ejecta, coupled with the object's small reduction in mass, could produce enough of a change in the object's orbit so that it misses Earth. Hopefully. Cross our fingers. Um, Another alternative uh, is to explosive deflection is to move it slowly over time. So a small but constant amount of thrust accumulates to deviate an object sufficiently in its course. So you can either use a whole lot of thrust right at the beginning, or you can use very little thrust over a very long period of time. If you've ever played Kerbal Space Program, you'll understand that concept. So um, let's see, there have been some proposals to use a large uncrewed spacecraft hovering over an asteroid to gravitationally pull the asteroid into a non-threatening orbit. Basically, you use the mass of the spacecraft with like an ion engine or something. It's moving along very, very slowly, but it's at the same time maintaining a certain distance above the asteroid just on one part of it, like in this image. So the asteroid is pulled very, very slightly towards the spacecraft over a long period of time. And we call it kind of a tractor beam. Not exactly, but it's got sort of the same effect, just over a longer period of time. So both objects are gravitationally pulled toward each other, but the spacecraft can counter that force by using its thrusters and ion engine. So the net effect is the asteroid is accelerated toward the spacecraft and deflected slightly. The spacecraft keeps going. Um, it's very slow, but it works regardless of the asteroid's composition or spin. Rubble pile asteroids would be difficult to deflect with nuclear, but it doesn't matter. In this case, it can go ahead and still be used. So this gravity tractor may have to spend several years doing this. But if you have enough of a warning ahead of time, 10 years, 20 years, there's plenty of time to do this. Okay. Other options, we can use mirrors in sunlight, lasers, ion beams to heat up part of the asteroid. Kind of like the nuclear option, it'd create an ejecta plume, a localized one, and that would act as an engine and push the asteroid. Um, we can drop a few rovers to land and start to break up the asteroid and make a way for them to fling those bits off at high speed. Again, Newton's law, you get a little push on the asteroid over time, it can change its orbit. We call that a mass driver. It's literally throwing rocks. Back to monkey, it seems. Again, with Newton's laws, we can drop some rocket engines onto a solid asteroid, cut out the long-term stuff. It's expensive, but the advantage is it's relatively fast. It might not be enough, though. There's another option. We can wrap the asteroid in foil, or mylar film, or we tether a solar sail to it. Let pressure from the sun push against it and deflect it slowly over time. The reason why you would want to cover it up is because you get, again, with Newton's laws, um, the asteroid itself is absorbing sunlight. Asteroids have a very low albedo, their surface reflectivity, they're just dark objects. So if you wrap it up in something shiny, or let's go back, because it's a dark object, it absorbs sunlight. So photons hitting it get absorbed. There is a slight push, but it's relatively constant. If you cover it up with foil, it's no longer absorbing those photons. The photons are bouncing off. When they bounce off, they impact more energy, again, Newton's laws, uh, giving it essentially a little bit more thrust um, from the sun itself. If we do a solar sail, then you wrap lines around the asteroid. I guess you could only really do this for a solid one. Wrap lines around it, put a big sail tens of kilometers across or more, and use the pressure from solar wind and light to push it away into a different orbit. So it's a quick overview of detection and mitigation. So let's see what happens when we don't. So at 10 meters, asteroids of this size impact Earth about once a decade. Very bright fireball, strong sonic boom, they can break nearby windows. Um, let's see. Uh, got a question from the chat. Is that really true? I'm not sure what what is actually true. If you can elaborate, I will answer that question. Okay. Um, so at 50 meters, asteroids like that impact Earth about every 1,000 years. They cause some local devastation. They may or may not have an impact crater. At 140 meters, it's about every 20,000 years. It creates a crater 3,000 feet to 7,000 feet across, 1 to 2 kilometers in diameter. The asteroid could cause deaths across metro areas and states, depending on the impact location. Asteroids this size and larger that come close to this orbit, we call them potentially hazardous asteroid or PHAs. 1,000 meters or a kilometer across. Asteroids like this impact every 700,000 years. This creates a 6 mile, 10-kilometer wide crater, and it causes global devastation, possibly the collapse of a civilization. 10,000 meters, 10 kilometers. That's estimated that it hits Earth once every 100 million years. They leave 60-mile or 100-kilometer wide craters. These are global devastation, mass extinction events. It kills off most life on Earth. And this is a picture of Barringer or meteor crater in Arizona. So it is officially called Barringer Crater because it's it's on land owned by the Barringer family. So the Tunguska event, what we are uh, what we are celebrating, is that the right word? Remembering on this day. This was a large explosion of somewhere between 3 and 50 megatons of the TNT equivalent. It occurred near the Podkaminiana. I don't speak Russian. I speak Polish. Tunguska River in what's now Krasnoyarsk Krai in Russia in the morning on June 30th, 1908. So it's the explosion over the sparsely populated East Siberian taiga felled a large number of trees over an area about 2,125 kilometers squared, or 830 square miles of forest. And there was eyewitnesses who said maybe up to 3 people died. The explosion was attributed to a meteor airburst. So the atmospheric explosion of a stony asteroid, we think between 50 and 60 meters wide, 160 to 200 feet. The asteroid approached from the east-southeast, probably with relatively high speed, about 27 kilometers a second. That's 98,000 kilometers an hour, or about Mach 80. It is classified as an impact event, uh, but the object is believed to just have exploded at an altitude about 5 to 10 kilometers up, about 3 to 6 miles, which is not a lot, rather than hitting the surface. So there's no impact crater there. It was directed mostly downwards, so unlike a nuclear detonation. So the Tunguska event, it's the largest impact event on Earth in recorded history, but we know much larger impacts have occurred in prehistoric times, including the Chicxulub impact that ended um, the Cretaceous period. An explosion of the Tunguska magnitude would be capable of destroying a large metropolitan city. So the equivalent Torino scale rating for this impactor would be an 8. Certain collision, local destruction. So in the morning, about 7:17 local time, Evenki natives and Russian settlers in the hills northwest of Lake Baikal, they observed a bluish light nearly as bright as the sun moving across the sky and leaving a thin trail. Closer to the horizon, there was a flash producing a billowing cloud followed by a pillar of fire that cast a red light on the landscape. The pillar split in two and faded, turning to black. And about 10 minutes later, it was reported there was a sound similar to artillery fire. Um, Eyewitnesses closer to the explosion reported that the source of the sound moved from the east to the north of them. The sounds were accompanied by a shockwave that knocked people off their feet and it broke windows hundreds of kilometers away. The explosion registered at seismic stations across Eurasia, and airwaves from the blast were detected in Germany, Denmark, Croatia, the UK, and as far as the Dutch East Indies, just now Indonesia, and in Washington, D.C. It's estimated that some places resulting shockwave would have been the equivalent to an earthquake measuring about a 5 on the Richter scale. So the area is so remote, it took until 1921 for Russian mineralogist Leonid Kulik to lead a team to the site, to the river basin, to conduct a survey for the Soviet Academy of Sciences. This was just after World War I and the Russian Revolution against the Tsar. Um, so everyone is a little bit busy doing things other than going to look for the results of an explosion in a remote, unfashionable region of Siberia. So, although they never visited the central blast area at the site, um, many of the local accounts were known, and Kulik thought that it was a meteoric impact that had caused it. So, upon returning, he persuaded the Soviet government to fund an expedition to the suspected impact zone based on the prospects of salvaging meteoric iron. So he went back in 1927. He hired local hunters to guide his team to the center of the blast area, and they expected to find an impact crater. But to their surprise, there was no impact crater at ground zero. Instead, they found a zone about 8 kilometers or 5 miles across where the trees were scorched, devoid of branches, but they're still standing upright. Trees further from the center had been partly scorched and knocked down away from the center, creating this radial pattern of down trees. And later expeditions found evidence of meteoric iron in the soil and embedded in trees there. So they also found silicate and magnetite spheres. So that gives some evidence to the asteroid impact um, hypothesis, as opposed to a comet. We wouldn't be finding metal in a comet, but we would find that in a stony meteorite. But it was most definitely not an alien spaceship. Let's see. Meteor crater, excuse me. It's northern Arizona to the west of Winslow, and it's formerly known as Barringer Crater after the family that owns the land. It is not public. It's not a national park. It's not a national monument. It is a private operation, but it is open to the public as a tourist destination, and it's an important educational and research location. It was used to train the Apollo astronauts for the moon landing, so they would know what it's like to be in a crater. And it's still used now for the asteroid corps, astronaut corps. Meteor Crater Visitor Center. It's located on the northern rim. It's open daily from 8 o'clock to 5 o'clock. If you do get to go visit, get there early and not at 4 p.m. like I did. I was there 20 something years ago, and I got to see just a little bit from the rim. I walked down to the viewing platform um, right over here, and that was it. And then it was closing. So, um, and the other times I was in the area, it was well into the evening. It was after they closed, so it was just too late to see it again. Next time I go out there, I'm gonna make it a point to be there early, see more of it. They actually do have rim walks. You can walk around the entire outer edge. There are also walks that go down into the bottom of the crater. So those just have to be planned ahead. I don't think it's anything like spontaneous. I think the rim you can do whenever you want, but going down the bottom, that's a planned event. So the crater itself is 3,900 feet across. It's 560 feet to the bottom. It doesn't really look that big or that deep for most pictures, but when you're there, yeah, it's huge. Um, I took this in 2003. Um, this bit right here in the middle is the old mining camp. See if I can get my bigger pictures here. Um, I think there was like an old RV or a mobile home there. I'm not, I don't remember exactly. Here we go. So zoom in quite a bit. Here we go. So this, I think, is this either a water tank. I think this is a water tank. I think this is the remains of the drilling platform, but this thing here, I believe, if I remember correctly, this was an RV that they had down there. People to overnight. I'm don't remember exactly. It's been 20 something years. But as you can see, this is a very, very large crater. You can see the layers in the rocks. Is this Coconino? No. I believe this is Toroweep Formation. This is the Coconino. Ah, it's been so long, I don't remember. No, no, wait. Well, okay. Coconino is in the Grand Canyon, and it's usually a paler one. So, anyway. Um, what you can see here, though, sort of, is this lip. It was actually blown up higher. Um, and you can see that in other images of the crater where the lip of it is raised before it goes back down. And that's typical of craters like this. There's a viewing platform right over here. So a little telescope so we could see all the way down to the bottom. And that's why I just have this memory of it being an RV, just being an RV down there. So I don't know how they got it down. Could be a trail. This may be a trail right here. Yeah. Anyway, if you have a chance to go, I highly recommend going. Again, 8 to 5. So what happened? The oh, let's see, where was it? Okay. Oh, hold on. There we go. So back in the late 1800s, scientists first became aware of the crater from settlers in the area and people passing through. And they thought it was well, some people thought it was meteoric, some people thought it was volcanic, like it was the remains of a volcanic steam vent that had just blown a hole through there. Um, and then in the early 20th century, Daniel Barringer thought this must have been a meteor crater, even though no one had proved that impact craters were a real thing at that time. So the common consensus was that the craters on the moon were volcanic. So he got a land patent. He staked the mining claim and he started digging. So his mining company found bits and pieces, even digging down more than like almost 14,000, sorry, 1,400 feet, 419 meters, um, but not the giant load that he thought must be there at the very bottom in the center. Um, Now we know that it was never there in the first place. So Meteor Crater is the best preserved large crater on Earth. We're just very lucky it's in such an accessible place. And it's open to the public, or at least the paying public, and it is available for research. The asteroid that created the crater, it impacted about 50,000 years ago during the Pleistocene epoch. At that time, the local climate on the Colorado Plateau in northern Arizona was cooler and wetter. It was mostly an open grassland, dotted with some woodlands, and inhabited mostly by mammoths and giant ground sloths. Humans did not arrive in the regions until tens of thousands of years later. So, other than the mammoths, there wasn't really anyone to witness the events. Um, in any case, you wouldn't want to be close enough to see something like this anyway. The asteroid itself was about 50 meters across, 50 to 60 meters, made of nickel iron, perhaps as little as 100,000 tons, perhaps as much as 300,000 tons. And its impact speed was 26,000 miles an hour, or about 12 kilometers a second. which isn't terribly fast. Not for asteroids and meteoroids impacting the atmosphere. But at that speed, about half the mass of the asteroid was burned away in the atmosphere. Most of the rest was vaporized, uh, and it melted upon impact. Very little remained in the crater itself. The largest fragment is the Hulsinger meteorite, and that weighs 1,409 pounds or 639 kilometers, kilograms. The crater was deeper in the past, but over time the edges have eroded and slumped down about 50 meters, and the eroded material has filled the bottom up by about 100 meters. So for the meteorite fragments, they're not called meteor crater meteorites, but Canyon Diablo, because the nearest geological feature is a small but long winding canyon to the west of the crater. We'll talk about why later. There are a lot of small fragments of Canyon Diablo meteorites, mostly shrapnel. Um, they're small pieces of molten, partially molten material that were thrown up to 20 miles away from the crater. It's covering an area about 100 square miles. You can find a lot of these online, just for sale. Just be sure to buy from reputable dealers. Talk about why later. Um, let's see. Okay, on to meteoroids. So that's the stuff that's smaller than asteroids. From grains of dust to pebbles, rocks about a meter across. This is the general debris around the solar system. Most of it's broken bits of comets and asteroids. They're either rock or metal or a mixture of the two. Because they're so small, it's very hard to spot them before they hit the atmosphere. But luckily for us, small stuff like this tends to burn up nearly completely. Only a few of the larger pieces ever make it down to the ground. Meteor showers, they come from the debris streams of comets. And we named them after the constellation that they seem to radiate from. Meteor showers can have just a few to tens of thousands of meteors visible in an hour. If there are thousands or tens of thousands of meteors, we call that a meteor storm. Nearly all meteors originate from comets. There are a few of these showers every year, and they happen at the same time of the year, um, as the Earth enters a particular debris stream. The big ones each year are the Perseids, the Geminids, Eta Aquarids, and the Leonids. And each have their own styles, personality, however you want to describe them. The Perseids, they're fast and bright, about 60 an hour, and they can produce fireballs. Um, they are coming soon, and the new moon will make them more visible, especially from a dark sky site away from city lights. The Geminids can be up to 120 an hour. They're bright, slow, and they can be very colorful. Eta Aquarids can be about 60 an hour in the southern hemisphere, 30 in the northern hemisphere. Oh well. Um, they're well known for their speed and for their glowing trains, and these come from Halley's Comet. The Leonids are usually only 15 an hour on average, but during a meteor storm, they can produce over 100,000 an hour. These happen about every 33 years when we pass through overlapping debris streams, but because of orbital mechanics, the next time that will happen will be in 2029. Um, sorry, 2099. So a ways away. Oh well. Meteors enter the atmosphere anywhere from 11 kilometers a second to 72 kilometers a second. So the one that hit Meteor Crater was coming in at 12 kilometers a second, relatively slowly. And it all depends on their orientation with the Earth at the time of capture. If it's coming up from behind, just kind of catching up, it can be the intercept velocity will be a lot slower. If it's almost head on, it's going to be much faster. So this is a video of a Perseid meteor in real time, about 1 centimeter in size. So like a small marble or just a piece of gravel. In less than a second, it burns up completely into dust at altitudes from 50 to 75 miles, 80 to 120 kilometers. If you have any questions or comments, you can go ahead and put them in the chat. And if you think about it, a tiny rock, the size of a pebble. I'm trying to find a pebble around here. I do have a pebble. A, a little rock this size right here burns up in about a second, but it is visible from more than 50 miles away. And if it's on the horizon, it can be 100, 200 miles away. But still, very, very bright, very visible. Fireballs. It's just a term for a very bright meteor, brighter than magnitude -4 or brighter than planet Venus. Um, they can last a few seconds and they can be colored. As they slow down, some of the brighter ones, they break off pieces and those bits and pieces burn up separately. Several thousand fireballs occur in our atmosphere every day. The vast majority come down over the oceans or uninhabited areas, and a lot come down during the day, and we just can't see them. Those that occur at night, these stand little chance of being detected due to relatively low numbers of people being out to notice them, except for we astronomers out in dark sky sites looking through telescopes. But I will say, I have not seen a whole lot of meteorites because I'm usually head down imaging, and people who are constantly at the eyepiece of a telescope are not seeing very many meteorites. But the ones who are just relaxing and sitting back and looking up with the eyeball Mark One, they see lots. Um, I remember there were many times when my wife and I went out to the club's dark sky site, and I was looking at charts or I was doing something, and then she would go, "Oh, meteor!" Ah, I didn't see it. "Oh, meteor!" Ah, I didn't see it. If you want to see meteors, don't look through telescopes. Just lie back and look up. Um, Nowadays, though, we can find a lot more because of technology. So, doorbell cameras, dash cams, security cameras, they're constantly monitoring parts of the sky that we're not really looking at, but the camera's seeing anyway. Um, and the security cameras are constantly recording, but they're only keeping differences. So when there's something bright in the sky, that's something different. If someone's walking in front of the camera, that's something different. That's what it records. That's what it alerts on. If no one is out in front of your house, nothing changes. There's no reason to record that. So, oh, and of course, people with cell phones. The best videos are people who set up dedicated meteor hunting cameras to record fireballs and bolides each night. Whoops, let's go back. There we go. So this was April 23rd, 26. So this is not too long ago. This is a fireball over Utah. And again, this is just a dash cam. They weren't planning on it, but there we go. This is the same one, different dash cams. And this is a security camera. See it exploding in midair. Someone's doorbell cam. Just have me point in the right direction. Another security camera. Same object, different locations, just happen to be pointing in that same area, just happen to be recording that night because they're either always recording or they just happen to be there, like for the dash cams. So bolides. Bolides are large fireballs that explode or break up in the atmosphere. Air gets into these little cracks or holes in the rocks, and because the material just really isn't that strong to withstand all those forces, they tend to break up into pieces or even explode. So these are large meteoroids or small asteroids that enter the atmosphere, and they can burn for several seconds or they can last for several seconds as they burn up. So I have a couple that I pulled from YouTube, and I gave credit to every one of these. This is a neat one. He seems to use several wide-angle cameras pointing at different parts of the sky, and then he saves the interesting ones. He's got several videos on his channel if you want to take a look. So right here, this trail, I'll play this again too. That wide trail that was there, that's just an artifact from the camera. So if we loop it again, this trail is probably somewhat real, but this wide part, that's just an image artifact. The way the camera records is it uses lots of different technology, including keyframes. But the idea is that it's trying to compress the data as much as possible, and it assumes that stuff hasn't changed as much as it perhaps has. And you can see this effect on some security cameras. Um, if someone, especially at night, is walking past the camera, it leaves kind of this ghostly trail right behind them. This is all that it is. It's just an image artifact. It's not actually what's there. This is one from the UK. No, sorry, this is one from Maine. And very nice, long-lived bolide. Looks like it came in on a very shallow angle into the atmosphere. It's steep enough not to bounce off, um, but shallow enough that I was able to go through a lot of atmosphere and last a long time. And again, they have a couple of videos just like this. Very, very neat. And that's all there was. This one is in the UK. This is a fireball. It's another bolide exploding. This is um, near the Scottish border, English-Scottish border. It's very bright. It's got multiple explosions, and then we're going to see this green bit. Oh, well, let's see. There we go. We're going to see a little bit of green bit. That's just a lens flare. It is not an actual like second meteorite or something tracking it or something. And you'll see exactly what I mean. So here it comes. And it gets very, very bright and explodes. And there we go. This is not a meteorite. This is a lens flare coming off of that. And it breaks up. Let's see that again. Appears very suddenly. As it's slowing down, it's getting brighter, 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 and blows apart. Blows apart again. And a little bit more. And a little bit more. And at the very end, you see that little debris trail coming down. Now, this is not just an exploding bolide. This is a persistent trail. It's a dust trail of ablated material that's left over after the meteorite's passage, lasts for several minutes after the meteor. So it's a very, very interesting capture. Um, Incidentally, we actually have been able to bounce shortwave radio signals off of these persistent trails and use them kind of like a almost like a repeater for shortwave radio. So a neat little bit of trivia there. So as it's going, kill that. It's going, going, going. There we go. Saw it right here. And it lasts for several minutes. Let's see that again. Remember, this is a time lapse, so it's very, very fast. You see that right in the corner. So that dust is being blown about by the wind. That is a very, very neat capture, and you're not going to be able to get that with a security camera. Oh, a couple satellites there too. Actually, a lot of satellites there. It's a problem that we have is a lot of satellites. Okay, Chelyabinsk Super Bolide. This is the one that exploded in 2013 over Chelyabinsk, Russia. It's on February 15th, 2013. And the whole thing, from the first brightening as it entered the atmosphere to the final shatter explosion fade, took 15 seconds. So this video was taken about 100 miles away from the ground track, and the trail is very low on the horizon, but still incredibly bright. So the asteroid is between 17 and 20 meters in diameter, about the size of a school bus, and we think it weighed about 10,000 tons. The estimates the final explosion was equivalent to a 500 kiloton blast of TNT in an airburst, and much, much smaller than the 3 to 50 megaton range for the Tunguska event. And I am forgetting something, and I have to ask for it. Let's see. Um, um, there we go. All right. Let's watch that again. It's such a neat thing to see. So this is a dash cam. Someone was parked, um, maybe eating dinner in the car, and there it goes. So here is the major explosion. There we go. So this is where it exploded. This is a mushroom cloud. So this video, let me see if I can desktop audio. I can get the sound for this. No, I don't think I have sound for this. Maybe there is sound. Oh, no, I think I have sound for this. But I think you'll know exactly when the shock wave hits. Everyone is staring at this, looking up, trying to figure out what's going on. There's a shock wave. Lots of broken glass, lots of injuries. Oops. So it took about a minute and a half for the shock wave to hit the ground directly underneath. About 25 kilometers away from the ground trace took about 2 minutes for the shock wave to hit, and 100 kilometers away took over 5 minutes. Chelyabinsk was about 40 kilometers from the center of the ground trace, and it took about 2 minutes for the shock wave to hit. People had gone outside. They wanted to look at the strange clouds left over. And when the shockwave impacted the ground, windows were shattered all over the city. Some buildings partially collapsed as well. Um, there were over 7,200 buildings in Chelyabinsk that were damaged. 1,500 people had to go get medical help for injuries, mostly from glass or falling building debris. So we can see the trail here with the large mushroom cloud here at the end. Um, this was the final explosion at this point. Okay, so I needed to get a couple things for later. There we go. Okay, and we can also see that the low angle of entry, there's a lot of time for the asteroid to slow down um, in the upper atmosphere. Had it come in steeper, it may not have slowed down enough, and it may have hit the ground instead of blowing up that high. So we can see the exosphere up high, the thermosphere, where, here we go. So troposphere, airplanes fly. Stratosphere, we send up high altitude balloons. The mesosphere is where um, asteroids and meteoroids burn up. Thermosphere, much higher, is the region where we keep a lot of our low Earth orbit satellites, where the space station is. And exosphere, geostationary satellites, probes, anything further out. Excuse me. Ooh. So, on the average, 150 tons or so of material falls into the earth every single day. Okay. Uh, most of it's small. It either burns up or falls into the ocean. 70% of the world is covered by water. So, that's where most of it is going to land. The rest of it falls on the land. Um, but we typically find places where we can find, sorry, we typically find meteorites in places where they're really obvious, where we can find them easily. And deserts are the best places to find them. So, if you have any questions, comments, concerns, go ahead and put them in the chat. We're going to start talking about meteorites now. So, meteorite falls versus finds. A fall is when someone sees a meteor, they see the trail, they calculate where it could have landed, and then they go out there and they find fresh meteorites on the ground. A find is just a meteorite that's discovered lying on the ground. But it's not known from a specific meteor event. It could be fresh, like some of these, or it could have been on the ground for 100 years or more, like this. Weeks, years, decades, centuries. When we find meteorites in the field, we notice them because they don't look like they belong. They stand out from all the other rocks uh, just nearby. So the deserts of northwest Africa, they're a great place to look for meteorites. The wind blows the surface sand and dust away, and it leaves what's called desert pavement. You can see this in this image right here. It's there's small rocks at the surface, compacted rocks and sand underneath, and it's hard enough that you can drive on it easily as long as you stay out of the dune fields, or the bottoms where sand tends to collect. Um, Meteorites have this dark surface on them. It's called fusion crust, uh, and they don't look like the rocks around them. Um, like in the Sahara, they tend to be lighter in color. The dark meteorites really stand out, and they're very, very visible. So notice these aren't in craters; they're just lying on the ground. By the time these impacted, they're only traveling 300 to 650 kilometers an hour, 190 to 400 miles an hour. They shed their speed very quickly in the upper atmosphere. They ablate up to 95% of their mass um, in like in the atmosphere before they even come down. So if you take a look at this one, this is what hit the ground. Imagine this being 20 times larger. So the rock that hit the atmosphere was 20 times bigger than this, and all that mass was ablated away, and just this little bit was left over. So, um, yeah, and fusion crust. So this is this dark uh, coating, basically, of melted material on meteorite. So by the time they hit the ground, they're just going at terminal velocity. Also, very interesting little bit of trivia. A meteorite that hits the ground almost immediately frosts over because the inside is still the temperature of space. So the passage through the atmosphere, it doesn't heat up the inside. All that heat is taken away by the ablating material. So the inside has, and it's so fast too that the inside just does not have time to heat up at all. Um, so this isn't like Hollywood when it hits the ground. Um, there's no fire, there's no smoke, there's no pulsating green glow. It's not like the movies. Hollywood adds all that for drama. Um, if you ever do see a meteorite plop down right in front of you, do not touch it, especially if it is frosty. If you do, you're going to get severe cold burns or frostbite on your fingers and hands. If you put your tongue on a metal flagpole in the middle of winter when it's below zero uh, or below freezing, um, it'd be like that, but worse because these are close to absolute zero. Um, well, let's call it just a couple kelvins. Let's say 5 to 10 kelvins, so very, very cold. If you look at both of these, they have GPS devices right next to them, and the location is blurred out for a reason. So Tomas and Marcin, like just about all meteorite hunters, they don't share the exact location where they found these. They give a at least publicly, they give like a general area, um, uh, accurate to within a few miles for the official records, but they may come back to the same area like years later to see if there were any meteorites that they missed. So these photos are done as in situ documentation. This is where they found it. This is the position of the meteorite when it was found, untouched. Um, in the surrounding area, if it is a crater, these are too small to form a crater. Um, they put down the GPS receiver, they take a picture, that's the documentation, and now they know which rock it was, where this rock was found. They can then pick it up, bag it up, and then they can label it and organize it and take it away. Hmm. I know, I saw. Go ahead. All right, there are two ways to classify and categorize meteorites. So, first method, primitive material versus processed material. Um, So, yeah, that's pretty much it. Both these are actually my meteorites as well. Primitive material, stuff that's basically been unchanged since the formation of the solar system. This is the oldest material in the solar system. It includes chondrites. Um, they're made from little bitty droplets of molten material. It's like the dust from the original uh, gas and, and and dust of the planetary protoplanetary disk that our solar system developed from. Processed material was part of a planet or an asteroid. Uh, oh, I have a question. Did I see the landing in Prince Edward Island recording with a safety camera on the house? Almost no noise. I didn't get to see that. I'll have to look for that. Um, okay, processed material. This is part of a planet or asteroid. It was heated, melted, changed in any number of ways, can be metamorphic. Uh, it tells us a lot about where it came from, but it's always going to be much younger material than that of the early solar system. Um, these two images are really interesting. On the left is a nickel iron meteorite sitting on the surface of Mars, taken by Opportunity, the Opportunity rover in 2005. And on the right is one found by Curiosity in 2016. I know you do. Um, Even on Mars, meteorites stand out against the landscape. So these two definitely don't look like the rocks around them. I mean, this one is really obvious. It just doesn't fit in with these guys at all. So we know they're meteorites because the rovers have laser and spectrograph instruments, and we're able to test them and find out they're made of nickel and iron. And because Mars' atmosphere does not contain oxygen, neither appear to be oxidized. Primitive meteorites. These are the remnants of the original solar nebula, and different types condensed at different distances from the sun. So they're very temperature dependent. Stony chondrites. They formed around the distance of the asteroid belt, and the carbonaceous chondrites formed a little bit further out from the asteroid belt. Primitive meteorites, they give us a glimpse into the conditions and the composition of the early solar system. Processed material comes from bigger objects in the inner solar system. Planets, dwarf planets, asteroids, they're big enough to be roughly spherical and with a differentiated crust, a mantle, and a molten core. Pieces knocked off these objects through impacts were modified from their original form, usually through melting. Metallic meteorites, like this one, they're fragments of cores of large differentiated asteroids that were blown apart in collisions. Other meteorites are pieces of crust material from asteroids, from Mars, from the moon, knocked off by impacts. The rocks traveled around and around the solar system, and eventually they landed on Earth. Chondrites are silicates with, sorry, achondrites are they're silicates without chondrules. The typical ones are is crustal material from the moon and Mars, and the HED group from the asteroid for Vesta. Nickel iron meteorites come from the cores of big asteroids, while pallasites come from the boundary layer, where the mantle of an asteroid meets the molten core. They kind of mix there together. Then we have mesositerites. They're from the period of planetary formation. They're probably created by low velocity collisions of large metallic core fragments from the surface of differentiated asteroids. These collisions reduce the mantles and the crust to small silicate fragments, but left the cores in the form of large durable metal pieces. But they're all fused into a solid mass. Really interesting. So let's go back to chondrites, the primitive material. Um, these are some of the oldest material in the solar system. Um, it's the most similar material to the early solar system. About 20 to 80% of the mass of a chondrite uh, is in these spherical millimeter scale chondrules. They're scattered throughout the matrix that holds them all together into one piece, one rock. In zero G, liquids tend to form spheres. So we think these are molten droplets at some point first condensing out of the birth nebula of our solar system and then melting before cooling into solids. When we compare the ratio of elements in the chondrites, they match really closely to what we find in the sun's atmosphere. And we see a lot of chondrites with shock features. We think they're from asteroid collisions. Um, we only have a few that really would we consider to be pristine samples. Achondrites, they're silicates from the moon, Mars, or Vesta. We have one meteorite which may be from Mercury, Northwest Africa 7325, but we can't know for sure because there's a lot of disagreement on what the chemical signature of Mercury meteorites would be. We just don't know. We have one sample, that's not really a lot. We have many from Mars, including this one here. It's called a Black Beauty, or Northwest Africa 7034. There are no Venetian meteorites because of two factors. One, it's a very, very high escape velocity needed to send a rock to Earth, and the very thick atmosphere would cause significant drag on anything trying to leave. So, if any of you have ever played Kerbal Space Program and tried to leave and take off from the planet Eve, you know exactly what I'm talking about. So there are primitive achondrites, which we think are the recrystallized chondrites, or some that contain relic chondrules that were partially melted within a few million years after the formation of the solar system. We can think of achondrites as rock samples from various objects in the solar system. Most of them are from massive collision on 4 Vesta. Um, so we have the HED group. The Howardites, this is a sample seen here. This is crustal material. Um, Eucrites are volcanic in origin. And then Diogenites, this is mantle material. We have shallow um, Diogenites, and we have olivine rich Diogenites, which are deeper down. Think of it just a deep mantle material, all from one big collision. Um, we have another method of categorizing meteorites. This one's by composition, what they're made of. And this is by far the most popular one for collectors. Um, Stony meteorites. These are chondrites, achondrites. They include, yeah, they have mostly silicate rocks. Some may have small amounts of iron for the chondrites, and very little to none for achondrites. And about 86% or so of all meteorites are going to be these stony ones. Carbonaceous chondrites, they're the oldest and rarest of chondrites. They're forming out past the asteroid belt where it was cold enough that carbon containing compounds could condense and not be in gaseous form. So they contain lots of organic compounds, including amino acids, fatty acids, other so called building blocks of life. Um, Panspermia is the idea that the building blocks of life originated in space and fell to Earth in the form of carbonaceous chondrites. There's a new paper, actually, it's not new anymore, it was released I think about 2 3 years ago, identifying the wide diversity of extraterrestrial purine and pur- pyridamine nucleobases in carbonaceous meteorites by Yasuhiro Oba from Hokkaido University. Previously, experiments had predicted that pyrimidines could be produced from chemical precursors found in meteorites, but we weren't able to find them. So they were able to detect nucleobases in 3 carbonaceous meteorites using new analytical techniques optimized for small scale quantification of nucleobases down to the range of parts per trillion, when we previously only been able to detect parts per billion. In addition to previously detected purine nucleobases in meteorites such as guanine and adenine, they were able to identify cytosine, uracil, and thymine, and some of their structural isomers. given the similarity in the molecular distribution of pyrimidines in meteorites and those in photon processed interstellar ice analogs. The researchers believe that some of these derivatives could have been generated by photochemical reactions prevailing in the interstellar medium and later incorporated into asteroids during early solar system formation. Basically, this study demonstrates that a diversity of meteoric nucleobases could serve as the building blocks of RNA and DNA in the early Earth. Next, calcium aluminum inclusions. These are small millimeter to centimeter scale flecks in carbonaceous chondrites. No. Um, where was I before I was interrupted? Uh, okay, here we go. So we they were some of the first salts to condense out of the protoplanetary disk. Using lead isotope dating, we get an absolute age of 4,567,300,000 years, plus or minus 160,000 years. We call this cal times zero, and we use that as kind of as basically the beginning of the formation of the solar system. Now, we used to think that these came um, from the supernova whose shockwave started the collapse of our solar nebula. Um, but new research has said that's probably not the case. So, okay, stony meteorites. Ordinary chondrites, they make about 80% of all finds, but we don't think these are representative of the composition of all asteroids. We think about 40% of all ordinary chondrites, they come from 3685 Bozhnikova, Bozhnem, Bozhnemchova. It's Czech. Bozhnemchova. HH chondrites come from 6 Hebe. OC chondrites from 243 Ida, maybe. The L chondrites from Eros flora and the whole flora family. And the LL chondrites, like Chelyabinsk, we think come from Itokawa. We know certain achondrites are from Mars because they have tiny inclusions that have elements and isotope ratios the same as the Martian atmosphere. Um, we know that because we've sent probes to Mars and measured it directly. When Apollo brought back rocks from several regions on the moon, we were able to compare them to rocks to meteorites that we suspected were lunar, and some of the achondrites match the rock types exactly. We'll get into that as well. Achondrites from Venus. They're from one or more major impacts. There was one impact about, I think, around 24 million years ago. It knocked huge chunks of the asteroid apart, and it created a group of asteroids we call the V types. They're just chunks of Vesta. Howardites, crustal material, they're silicates. Eucrites, it's magma material from the mantle. Think of things like volcanic magma that cooled below the surface. Diogenites, again, mantle material. Olivine rich diogenites, they're from the deeper mantle. Nickel irons, these come from the cores of large differentiated asteroids that broke up. These lines that you see, it's called the Widmanstatten patterns. They're crystals of nickel iron. When an iron meteorite is cut and polished, is treated with nitric acid to remove the surface oxidation, and then when it's all cleaned off and neutralized, this is what you're seeing is the interleaving of kamacite and tannite bands within the sample, and different meteorites have different patterns, and the patterns are there. Um, well, okay, all these structures they form under really specific circumstances. So it's a slow cooling over hundreds of thousands to millions of years, uh, deep within the cores of these asteroids. We can't replicate this on Earth in a lab, um, and so this is actually a good way to test to see, is this a meteorite? Do you see these patterns? If you do, it's definitely a meteorite. You also check the nickel content. If there is nickel in it, it is likely to be a meteorite. If there's no nickel in it, it is very unlikely to be a meteorite, specifically a nickel iron meteorite. Stony irons, they're a mix of silicates and iron nickel. So what we see here are the mesositerites, and well, the two that we see are mesositerites and the pallasites. So the mesositerites, we think they're from low speed collisions between silicate asteroids and iron cores of broken up differentiated asteroids smashing together um, fairly slowly. And pallasites are olivine crystals in a iron matrix from that interface layer of the molten core and the lower mantle. Um, if you cut them through thin enough, you can see the light passing behind through the olivine. They really are the prettiest of meteorites, and there's a lot of jewelry made out of them. You just have to be really careful. There are several. There is one from China, and I can't remember what it's called off the top of my head, but it is very popular in jewelry. However, it has a lot of chlorine in the matrix, and it oxidizes very, very easily in a humid atmosphere. So you may buy a nice pendant, put it away in your jewelry box, and if it's not properly treated, if it's not properly sealed, you may come back 6 months or a year later, open up your jewelry box, and you have a pile of rust with some crystals in lying in it. So buyer beware. Okay, meteorites are important so that we can study the solar system. Meteorites come from specific locations like Moon, Mars, asteroids. They tell us about those worlds. Think of it as a free sample return mission. You just kind of get something, but it's random, just luck of the draw. You don't know what you're going to get. On the other hand, chondrites and primitive achondrites, being much older, are time capsules from the very earliest moments of the solar system. How do we know where meteorites come from? Uh, we analyze the light reflecting from asteroids to determine their composition. Um, Different minerals reflect light differently. So if you have a sensitive enough instrument, you can graph the reflectance versus wavelength, and you get a chart like this. And you can do the same with meteorites in the lab. They're just right there in front of you. And you compare the results. In this case, we have a carbonaceous chondrite called Renazzo, where it fell in Italy in 1824, and the asteroid 2 Pallas. The two plots are very similar, and this asteroid is tentatively the source of this meteorite based on this data. So, American Meteor Society, they track fireballs and bolides around the world. If you have a video you've taken, you can submit it to add it to the database. The more observations, the more accurate we can find the track of the meteor. So once a track is calculated from the observations, you can kind of figure out where the strew field, where the landing point of any leftover material, any bits and pieces may be on the ground. Um, Looking at this map, you might think the strew field is around Rush Hill, right there. That may or may not be the case. Remember that meteors are high up in the atmosphere. So this line here is the visible part of the track, about 50 something miles in Missouri, projected down onto the surface. The red point is where it stopped being visible, not where it necessarily landed. So by this time, it's slowed down only a few hundred miles an hour. There's Rush Hill. It's slowed down a few hundred miles an hour. It's probably ballistic at this point. If there are winds, they can push it in any direction. And remember that winds can vary in intensity and direction at different altitudes. So high level wind from the west might push it back toward Middletown. But a strong warm front from the south at lower altitudes could push it north again. So depending on the winds, it could be anywhere in this area, maybe. So where are the best places to find meteorites? Actually, let me go back one. Um, so quick story. In the early 2000s, we had a bolide over the North Texas area. And I believe it was two or three of our club members at the Fort Worth Astronomical Society went down to the Granbury area from Fort Worth and went around to some gas stations and were asking people, "Hey, did you see the meteor, the fireball last night?" And some people said yes, and I saw it here, and it started over here and it ended there, and it was about this high in the sky. Right? Well, they went to a different place. Oh no, I saw it over here. And it was at this point, and it went down this far. It was almost directly overhead, and it went down this way. And once they had some of that data, they were able to plot it on a map to see roughly where they were going, where this meteor, where this bolide was coming down. And when they had that area, they went out there, um, and they were mostly cornfields, just grass fields, some forest, but there was a road going through there. So they started walking the road, looking down and just walking the road for about, I want to say it was a mile and a half. And they found three meteorites, really, really tiny ones. Don't know, may have something that small. Basically little pebbles, but they managed to find them on the road and they tested them with a magnet. That's how they knew. So very small fragments, but they were able to find them by triangulating from reports just like this. I haven't done that yet. Meteorite hunting. What are the best places to find meteorites? Where they're going to stand out. Uh, so meteorites tend to be dark. So if you want to find them, you have to go to some place that's really obvious. Uh, Rocky deserts, Antarctica, Greenland. They're good places to look. Sandy deserts tend to swallow meteorites. They get covered up and they disappear under the sand and dust. And probably, possibly not too long after impact. It depends on the desert. Oh, excuse me. Um, Forests and farmlands, they're bad places to find meteorites. If a rock falls in the forest, does anyone really see it? If you saw a rock like this sitting by a tree, um, as you happen to walk by, would you notice it? Would you pick it up? Probably not. Um, it could be covered in leaves. If you find a dark rock in a cornfield, are you gonna be able to see one in a cornfield? Again, probably not. Unless you know one is already underground and use something like ground penetrating radar or magnetometers to find them, like the Brenham Palisade in Kansas. Um, that one was found several yards underground. Various pieces were found several like yards underground in a cornfield using the instruments that detected the iron in it. And we knew about the Brenham Strew Field from history. We knew where to look, but randomly looking for rocks in a cornfield isn't going to help you. We have to use those instruments in order to find them. So, only in specific circumstances would you look in a forest or in grasslands or a lake for a meteorite, and that's if you actually saw it landing there. If you saw a big splash in a lake, it's probably a fish and not a rock from space. Let's see. All right, here we go. Um, but it's just unlikely you're going to stumble upon a meteorite if you're not going to be looking for it specifically. And going through your backyard trying to find a meteorite, likely to be a waste of time and just exercise in frustration. So, uh, instead, a great place to look for meteorites is Antarctica. A dark rock on the ice really stands out. It looks totally out of place. It just does not belong there. The movement of the ice also takes meteorites and deposits them in these big batches at the edge of the ice. Someplace in Antarctica that are really famous for the meteorites are the Frontier Mountains meteorite trap and the Allen Hills site. Um, Allen Hills was location of the meteorite that was thought to have Martian fossils, if you remember that from many years ago. On the left, um, every one of these red flags here is a potential meteorite. So each one is marked, photographed, exact location documented. Then it's bagged up and labeled for later analysis. This one, well, yeah, you see a black rock sitting out on the ice. It just doesn't belong. All right. So let's say you found a weird rock in the backyard or grandpa's old wooden curio box, or you won it off a mysterious stranger with glowing eyes in a game of poker. Did you find a meteorite? Probably not. So let's go over what a meteorite's physical characteristics are. Does it have a dark fusion crust? Is it smooth? Does it attract kitchen magnet? Um, does it feel heavy for a rock its size compared to Earth rocks? Irons are typically 7 to 8 grams per cubic centimeter. Chondrites, usually 3 to 3.6 grams per cubic centimeter. Most silicates on Earth, they're about 2.6 to 2.7 grams per cubic centimeter. So if you're holding a meteorite, it just feels heavier than you would expect holding an Earth rock. It just is the best way to describe it. It just feels heavier because really it is. It's more dense. All right. Just because it's heavy, just because it has a weird surface or it attracts a magnet, doesn't mean it's a meteorite. Hematite concretions, they're iron rich. It's magnetic. It can look lumpy and weird with a shiny surface, but it's an earth rock. Some volcanic rocks are smooth. Some stuff like scoria or pumice, like these, they look really weird. Um, there are very few meteorites with holes or voids. There are a couple, but not very many. Um, there are a few basaltic lunar meteorites and rocks brought back from Apollo that have these holes and voids. Um, and there are some vesicular diogenites from Vesta, but they're all very, very rare. Iron slag. Uh oh, that's not good. Hang on one moment. Yeah. Well, this is always lovely to have a crash. And I jump to the last one. And I go through everything again. In the meantime, any questions, comments, concerns, ideas, things you want to share? If you put them in the chat, I can bring them up. But oh man, at the very end too. Okay, almost there. I was doing so well. There we go. Yeah. So iron slag, waste product of making iron and steel. It'll attract a magnet. It can look shiny. It can look dark, weird. It is trash. Show you why in a bit. Um, I've heard stories about people seeing meteors when they were kids. Uh, I was at a public star party, and someone came up to me with a story, and they said when they were a kid, they were out in the country on the family farm, and they saw one streak just over their heads, and then they heard it crash in the trees at the edge of the property. Um, but they were still upset because their dad wouldn't let them go at night looking for a meteor in a dark forest. Um, did he see it? Oh yeah, he definitely saw a meteor. But again, it wasn't just over his head. It was 50 to 70, 80 miles up high. And the commotion from the tree line was probably just a coincidence. I mean, we're in Texas. If I hear something going on the tree line, my first thought isn't meteorite falling, it's armadillo. Why? Because I've seen lots of armadillos going through the underbrush, going through crunched up leaves, and being a lot louder than you would think for their size. So, yeah, when I explained to him what probably happened, what probably was going on, he was disappointed. Hey, because that's a great story from his childhood, and I kind of ruined it. Um, but isn't it better to know the truth about something than to, live as an adult in a childhood fantasy, actually understand reality? Um, he was disappointed, but I don't think he was upset. And we kind of have to balance that fine line. We can't tell people, no, your ideas are bad, um, but we do have to work to correct them when what they remember isn't probably what actually happened. And we can give them an alternative explanation for what they saw, what they experienced, so they can understand it more fully. As new information comes along, I try to incorporate it in my presentations. I have to adapt and change what I say because what we know now is better and more accurate than what we knew in the past. And I want to know more today than I did yesterday. And I want to know tomorrow more than I know today. I try to maintain that philosophy in everything I do. Try to pass it on to my kid. It seems to be working so far. He was interested for a while, but it is getting late and he should be in bed now. So let's get to looking at actual meteorites. So these are, according to my wife, these are all technically his. I'm just holding on to them for a bit until he gets older. Uh, let's see. Here we go. So what are we going to show off? I have a number of meteorites. So we can start with, uh, yeah, let's do that. Let's start off with general meteorites, what they look like. And a big pile is usually a good way to start. So let's do that. Here we go. Big pile of meteorites. These are all rocks from space. They're all different. Different shapes, different sizes, slightly different colors, but all roughly fairly similar. Let's see, there we go. Let's push these out of the way. Start with one at a time. This is the very first meteorite I ever got. It is a unclassified Northwest Africa. Unclassified means it hasn't been cut open, hasn't been analyzed, has not been sent out to a lab, but it was found in Northwest Africa. Um, what typically happens is you have people like Thomas and Marcin who they go out, they will rent a couple Hilux trucks, Toyota Hilux. They will drive through areas in search patterns, just like a big square search pattern. And what they will do is one person, whoever's driving, looks ahead. Someone is in the passenger seat and they're looking to the right, and someone else is behind and they're looking to the left. And what they're looking for is rocks out on the surface that are standing out. If someone sees something, they just shout it out. Everyone stops. They get out. They check. Is this a meteorite? Does it look like a meteorite? Go ahead and start processing it. Cool. Pack it up. Um, get back in the trucks. Keep on going. Continue the search pattern. Don't just stop because you found one. Continue the pattern. Keep looking. Keep looking. Um, a while ago, and I think it's still done, um, the meteorite dealers in Morocco would pay uh, nomads, pay people. Night, love you. Mm, this one's mine. Okay, off to bed. It's 10 o'clock. Close the door, please.
Good night, everyone.
Go home. Bye bye. What was I saying? Oh yeah, the Berbers and other nomads that were traveling across the desert, uh, the meteorite dealers in Morocco would tell them, "Hey, if you see a rock like this," and they would actually give them like a sample of rocks, so a sample meteorite, so they would know what to look for. If you see rocks like this as you're going along in the camels, if you pick them up and bring them back to me, I will pay you money for them. So they would typically get, maybe 10 cents a gram, um, you know, if that, maybe $1 a kilo or something. But it was money that they could get just for picking up rocks, and the dealers would then sort through it, figure out which ones are interesting and maybe worth a lot of money, and go ahead and send those off for analysis. There's a university in Germany that does it. Um, and if you find a meteorite, you can send it to them. They'll analyze it. If you have the provenance of it, you can get it named. Um, and meteorites are typically named for the nearest geological feature, so it's not going to be named after you. But let's say it landed. Let's say it landed in Fort Worth. There was one that did it. Um, it broke up into three pieces, and only two have been found. There's one missing somewhere, and it's the Blue Mound meteorite. Why? Because Blue Mound was the nearest geological feature, and also town name, um, now where it was found. So that's what it gets named after. Well, the Sahara, Northwest Africa, doesn't really have a. It has a lot of geological features. They're just not named because, well, nobody cares. Nobody lives out there. It doesn't matter what this hill is called. It doesn't matter what this cliff is called. So those rocks are all called generally Northwest Africa, and they get a number. So these guys are unclassified Northwest Africas. You can see this one is a little bit different in terms of color from this one. So they're just different rocks, but they have this dark fusion crust on them. And the fusion crust is very, very thin. We'll get into just how thin it is, microns, and show you exactly how thin they are. So this one, it's kind of neat. This is partially oriented. You can see this part is very, very smooth. It's very, very shiny. If I turn it over, part here is pretty matte. The chip that came off of it. So what this tells me is that this rock was somewhat pointed down, maybe tumbling a bit, but mostly down in one direction as it traveled through the Earth's atmosphere and slowed down. And parts of it chipped off. So the chip here broke off in the atmosphere, but there was still um, enough air, hot air around it, that it did create a somewhat thin, sparse fusion crust in that area. So this is 280, about 285 grams. I'm remembering it. I'm not weighing it with my hand. I'm not quite that good. But it is very heavy for its size. Um, and again, this is the first one that I ever got. I saw it on cloudynights.com. This is an astronomical forum and classified section. And I thought it was really, really cool. And it was a gentleman in Canada who was selling it. This is really, really neat. I don't have a meteorite. So I went ahead and got it. Thought it was really cool. And I took it out to a lot of outreach events for the club. And I thought it was really interesting too. And then more and more and more. So now I have a fairly extensive meteorite collection. And this collection, it does go out to public outreach events. So we have club members who will borrow the kit, they'll take it out, and it is available for people to actually handle. You can actually touch these meteorites. Not all of them, but a number of them you can touch, you can hold, and you can feel the differences. So this is the first one. This is unclassified Northwest Africa. Once I'm done with, I'll put it here. These I got from the same dealer later on, and I actually asked him, "Hey, do you have any really nice ones I can use for outreach?" And he goes, "Well, you just said the magic words." And he sent me a lot, so more than I was expecting. And what he said was he had these sitting in the back of his closet for years, very, very nice ones. He just didn't know what to do with them. He just didn't have an opportunity. When I said, "Hey, I want to use them for outreach," he was more than happy to send them to me. So that's what I do. These are available for people to see. So again, it's very, very heavy for its size. And if I take a magnet, this is just like these little bitty magnets, I just put it there. It's sticking to it. Because there's a little bit of iron in here, and it just sticks. It's doesn't fall. Shake it, It's still on there. So, and parts of it aren't as magnetic. That one doesn't seem as magnetic as the top. That one's a little bit more. And if you hold the magnet and kind of just move it along the surface, you can feel difference. Oh, right there. That was a difference. There's like a chunk, a larger piece of iron right there. That's not over here. This is barely anything. This is like a strong area right here. So it's kind of neat things you can do with it. All right, next rocks. This one, smaller. It's got a nice shiny fusion crust. It looks pretty. Again, unclassified Northwest Africa. But when I flip it over, what's that? That is not a smooth surface. That is fairly rough. So what this tells me, there's a crack in here as well. So this tells me a couple things. As this piece was going through the atmosphere, it broke up. So it broke up high enough that there's still fusion crust on here. So it's still glowing when it broke up, like a bolide. And it developed this crack in here as well. You know, you can see the crack, a little hole in there too. That is not from impact. That's a crack, apparently, in the atmosphere. But it just didn't get inside to break it open. Maybe it did. Maybe there was a crack on this side, and that's what caused that break. In any case, this is a little bit of debris from the trail of bolide. Every meteorite has a story to tell. Here's just a bunch of different ones. They're very nice. They're just all different. You can see again, this is a broken piece. And again, magnets stick to it. Broken piece because this does not have a nice, shiny fusion crust on that side, but it does here. So again, this is probably, because it is so jagged on this broken part, this probably is also part of a debris trail that broke off the main mass, but it didn't glow for very long. So there's a little bit of fusion crust on there, but very, very little, and not enough that it would ablate a whole lot and smooth out the features. This one's very shiny and rough. Again, ooh, there's a right there's a shiny piece of iron. I can. There's not a whole lot of iron in this one. Just sticking very, very little right there. Just such a tiny amount. Maybe, yeah. See, it's still sticking, just not very much. And only in this one spot. And right there as well. On here, this part was cut and polished. So if I turn it just right, maybe able to see a little bit of shininess right there where the nickel iron flecks are. You can see them right there. So again, bits and pieces that fell off of bolide. This one, yep, again, shiny, kind of dull. These are all just broken off bits. This one, I haven't seen this one in a while. This one was cut and polished just slightly just to see what the inside it was. What is this? Oh, just some polish. And it's got cracks in it. But this appears to be, well, I don't know what it is. It's just another Northwest Africa unclassified. I would have to polish this a lot more to see exactly what the inside looks like. But again, it's nice, it's neat, and it's a lot heavier than you would expect. One more of these bigger ones. So, well, relatively big. This one is weird. Flat. It's mostly flat. When I turn it over, it's flat on that side. So it just, when it came down, it just came down in a very weird way that made this flat meteorite. And it's got some cracks in it as well. See the cracks there? So something happened. And this one, it seems like it expanded because if you look at it, the crack goes around it, and there's stuff on the inside. It's probably sand um, that was wedged in there. Um, I haven't picked that. I haven't analyzed it because I don't want this thing to break apart on me. Um, but yeah, it's got this weird crack in it, and it's got this weird, interesting shape. Again, every meteorite tells a story. I have one here. This is also a meteorite with fusion crust. However, if you look at this fusion crust, it's very, very matte. Um, it's got this weird reticulation pattern on it, um, but it's still fusion crust. And the difference between this one and the others, put one of the others next to it so you can see the difference in shininess between them. Um, the bigger one was out in the desert for 50 years, maybe 100 years, don't know, but it's been a while. And the winds of the Sahara just sandblasted it and left a very thin, even thinner coating of the fusion crust, um, but took off enough of the material to make it very matte and no longer shiny at all. But here's a neat thing. This is two pieces. I have two pieces of the same rock. I actually have this one. This one was my first one. And then I saw that the same dealer had this larger piece for sale. And I was looking at it and I thought, well, that's the same rock. It's hard to see here. But these lines, hey, there we go. These lines here, these cracks, they're not cracks. Turn them, you can see they're actually ridges. These are metamorphic. These are areas where sometime in the past, this rock was part of a larger asteroid. Something smashed it. Something smashed it so hard that it squeezed the rock together, cracked it along those lines. It melted along those lines and then refroze as harder material. This was one rock. Oops. I'm going to break my table. If I can get this fit together. There we go. Okay. Ugh. Scratched my table. Oh well. Things we do for science. This is the rock. I'm actually missing a piece in the middle. This doesn't fit exactly. There's probably this one slice, not that big. Maybe I can go this way. There we go. There's one slice here in the middle that's missing. Okay. I don't have that one. Someone else has it. If you have it, you see this, please let me know. And you'll know it's your rock because of the inside. But before we do that, this part here broke off, and it broke off very, very late in the train. And we can see that because there's little bits of fusion crust all over this, but not that much. Not that much at all. Instead, it's the inside material, untouched. Just barely kissed by the flames of passage through the atmosphere. And what's really interesting is we'll look at the edge. I have to refocus. Let's see. Back to here. Here we go. Refocus on this thing, and I hope I can get a close enough focus. There we go. Getting there. There we go. That's as close as I'm going to get. If you look at this fusion crust here at the edge, one is shiny, one is not. Why? Really easy answer to that. Because when it landed this rough side down, and it impacted, and it buried itself somewhere in this missing slice underneath the surface. Or sand blew up around it and it made a little hillock or something where the bottom was protected from that constant wind erosion, but the top was not. So the top got sandblasted, the bottom was protected. It is the same rock, and I'll show you why we know it's the same rock. As I put this down, become really obvious. Let's refocus. There we go. That's the same rock. Not only the outside shape of it with that missing slice, the interior cracks. On here, the cracks match up to the outside. In this darker area, this is all metamorphic rock. These are all places where the material melted and then resolidified and was made harder. And these shiny little bits, all those shiny little bits, that's iron, nickel iron. I can just drop it on anywhere and it's sticking. It's not rolling off, it's staying right where it is. Same thing on the other side. You just drop it, it stands up. Drop it, still stands up. It won't roll off. Okay, at least not very far, because it's being trapped. It's holding on to that little bits of nickel iron. So there is some controversy now about using magnets to test meteorites because there are some researchers who are looking at paleomagnetism of meteorites. And the fear is that if you use a magnet to detect uh, any nickel iron inside of a rock, you can change that paleomagnetism. Um, yeah, it may be a big deal. I don't know. But for amateur meteorite collectors, this is still a good way to do it. Um, some of the ones that I know actually have these little magnets on a thin string that they keep around their neck, almost like a thread. And the reason why they do that is so uh, they can bring a rock to it or hold it out to a rock, and the mass of the string is or thread is negligible compared to the magnet. So even very small amounts of nickel iron they would be able to detect. All right. So I really like this one. It's very, very neat. It tells a story of what happened to this rock sometime in the distant past. Again, this could have been 4.5 billion years ago. This could have been 2 billion years ago. This could have been a million years ago. And I do not have the resources to find out, but I'm pretty sure you can date metamorphic rock in. You can. You can date metamorphic rock on the remelting. I don't remember what the dating method is, but I remember you can do it from geology. Actually, do I have my geology? I may have my geology, old college geology textbook somewhere over there, but I'm not going to get into it now. Okay, so this is also Northwest Africa unclassified. It's just really neat. I should send this thing off for analysis. That would be really cool, but I don't have a provenance of exactly where this was found. Um, it would just have to be, hey, unknown. Um, yeah, just unknown. This thing fits together really, really well too. I mean, there's the shape of it. There's just this shape of it. It's just fits really, really well together. Curve over here. See, it's missing that slice, but it's a this rounded area right there is actually pretty good. So yeah, it's this is the same rock. All right, let's get into some named stuff then. Um, Here we go. Do I want to do that? Yeah. Well, how about this one? Because I can never remember what this is called. I'm gonna have to dig it up. One moment. And that is this guy. Get good focus on it. There we go. So you can now see the Windman-Stutton pattern of, let's see, meteorite and Scandinavian. So I can't ever, it starts with an M. Ah, Muon Muon Ian Alusta. Muon Ian Alusta. There it is. Landed northern Scandinavia, discovered in 1906, oldest known meteorite on Earth, landing about or falling about 1 million years ago. Um, it is 8.4% nickel, 91% iron. So it is a very, very pretty pattern on here. You can see the rust. It's iron. It's going to rust. There's nothing you can do about it. But it is a very, very neat rock. It is a rock, even though it is a hunk of iron. Yeah. And so this pattern, again, you get it by cutting the rock or cutting the meteorite, you polish it, and then you treat it with a nitric acid solution to bring out the crystals, and then you very quickly neutralize and clean it off. It is it's used a lot in jewelry. A lot of this was found on the ground, so um, there's just a lot of this material. This is a nice slice, and turn it over. You can see it on the pattern on the other side. And again, this takes hundreds of thousands to millions of years of slowly cooling down the iron core of an asteroid. We just can't synthesize this in the lab. Um, but it's a very, very neat one, and we will come back to it in just a bit. Let's start looking at some other stuff. Here we go. This one, in the case, I have to get it out. This one is a named one. So if you are at your computer, and if you like, you can actually bring up this meteorite and type in Northwest Africa, or NWA 10331. NWA 10331. Like I'm doing an auction. This is primordial. This is very, very old. This dates from early solar system. Um, it is a chondrite. It has a lot of nickel iron flecks in it. So if I put that down there, it stands up very easily. And then as I'm moving it across, I can feel every little fleck. It's very weird. It's jumpy. So if you have a meteorite like this and you take a small magnet and you run it along the surface like this, just running it, it's jumpy. Doesn't matter how smooth it is, doesn't matter how polished it is, because you're picking up all these little flecks. And if I do this, you can see the flecks there on the left-hand side as the light is bouncing off of it. And what I'm actually going to do, yeah, let me grab another light. So many lights. Okay, I'm going to grab another light here. We're going to switch it to, there we go. I'm going to take a different color. See how well this works. Not sure. First time I'm doing this. Intensity. See how well this works. So there we go. See all those blue, those shiny blue bits? I think those are showing up. All those shiny blue bits, that's the nickel iron. Okay. It's reflecting the light from uh, my little light. I can tune the colors on this thing too. Let's see if I can do a different. Oops. See if I can do a different color. It's going to stand out more. Purple. Maybe purple. Let's do purple. Yeah, purple. There we go. Purple really stands out, doesn't it? Hoping it stands out with YouTube. Um, yeah, all that shiny bit, that's nickel iron. There's quite a bit of it. Right here, right there, there's a little concentration of a couple little bits there. And if I shine the light, you can see them right there, that shiny bit. So this is an important rock. Um, it is, well, relatively important for meteorites. So this is one of 4 slices of this particular rock of Northwest Africa 10331. My dealer has one. Uh, Someone else got another slice. Um, I have one, and then the 4th slice was with I think uh, Tomasz Jakubowski, and he was last time I heard this several years ago. Um, yeah, this is several years ago, and he had given the slice temporarily to a Polish grad student who was doing research on early solar system materials. So it is it's a very neat rock. It's very interesting, and I think something like this is really cool. And my policy has always been, if I have something that you would like to borrow, for especially for research purposes, just let me know, and I can make it available. You can see all the little iron bits shining in purple. I think purple's a really good color for this too. It really stands out. So a lot of nickel iron in this sample. So again, Northwest Africa 10331. Now, I none of my meteorites are for sale. Uh, Once I have them, they're mine. But they're always available for public outreach, so any member of the club is welcome to ask, and borrow, and take them out and use them to show people. Show people things like, actually, you know what? Yeah, let's do that. I have an idea. Okay, this is Canyon Diablo. This is a piece of shrapnel from the meteor that impacted Meteor Crater in Arizona that we talked about earlier. Again, it's called Canyon Diablo because that's the nearest geological feature. It is not the Meteor Crater meteorite, it is Canyon Diablo. This is a neat piece of shrapnel. Flip it over. It's not exactly sharp. It's got some sharp bits, like protruding pieces, but this is strongly attracted to the metal. This is just a hunk of nickel iron. It's just, I can hold this thing up using the magnet. But I don't like this view. I don't like the way this looks. So we're going to fix this. Are we going to fix it? I'm going to put a different lens on this camera. So if you'll bear with me for just a moment, I got all this planned. Right now I'm using a 35 millimeter wide angle lens, and this one is lets me focus down to about a foot, but it is big, it is heavy, it is very neat. It is a cinema lens that we're using for a project, and now I'm using it to show off meteorites. And we're switching to a 90 millimeter macro. We're going to be able to see some real detail here now. Once I get it on. once I see where the marks are. There we go. I just have to do it very, very safely. Nothing falls. All right. Well, that's much better. And focus and light. There we are. Okay. Switching back to camera. That's much better. Much better image. Really zoomed in. We can really see some of these details. It is a hunk of iron. This was blasted out from the crater when the asteroid impacted meteor crater and created it. And the Strew field, well, sorry, it's not a Strew field. It is a ejecta field. It's about 100 square miles in Arizona. So if you go out there, you may be able to find one of these lying on the ground. It is entirely possible. Um, Thinking about it, if you took one of those magnetic shop vacs, it's not really a vacuum. It's like a kind of like an old timey um, uh, grass lawnmower that used blades, except this time it has magnets in it that can pick up debris on the ground. If you run one of those over a large area, you may be able to find bits and pieces like this of Canyon Diablo. So really, really neat. Um, and this was found, well, it says 1891. I'm not exactly, I think that's when the first Canyon Diablo meteorites were found, was 1891. I have these, let me show you this. I have these in little jewel cases. And the reason why I do this is I have these in display cases. They're actually uh, right back here. And this makes it really easy to take out to two events. Uh, have the meteorites there. I can pull out which ones I want to display, and the rest stay in the box. Um, but it's a neat way to keep track of them, and I put a little label on them, so it's really easy to see what is what. Ah, ah, Chelyabinsk, Chelyabinsk from Russia. So I want to open this one up. This one, you can see, it's a little piece of gravel. That's all that is. Little piece of gravel. It's a little chip on the side. Very, very small compared to my fingernail. But it is a meteorite. Got that little chip on there. And if I take a magnet to it, it does stick. So it's got a little bit of nickel iron in it. And that white inside, that's actually what it looks like. That's the material, the LL chondrite type. So some of the fusion crust just broke away, chipped away. Maybe it was in a box with other rocks or something. I don't know. All I know is that part of it is chipped away, but I have this little piece of Chelyabinsk. Now, I actually have a second piece of Chelyabinsk. This one is neat. I love taking this one out because this shows human ingenuity. What is it? It's a little fridge magnet with a piece of Chelyabinsk at the head. This is a piece of Russian folk art. There's an artist in the Chelyabinsk area, and he um, he found several pieces and carved little refrigerator magnets, little meteorites like this, carved them out of wood and painted, and then glued on a little piece of Chelyabinsk on the end. He sent this to my dealer, and my dealer said, "Hey, would you like this? This is really cool for outreach." I said, "Absolutely, that's fantastic." So um, it does not sit on my refrigerator. It goes out in public so people can see. You can just create art out of meteorites. Someone had this a brilliant idea of actually making a little wooden meteor and putting a real meteor at the head. I've never seen anything like this before, but I have this piece now. And again, it's just a really neat idea. And it's a real meteorite, tiny little piece of Chelyabinsk. All right, let's keep going. I'm gonna put everything onto the side that we've seen already. I can always come back to if necessary. Um, nickel irons. Speaking of nickel irons, so I have additional ones. This one is called Morosco. Morosco is a Polish meteorite. This one is all cleaned up and it's fairly shiny. It's not polished, it's just cleaned up. And it's a chunk of iron. It just sticks to it. It's all it is, just a chunk of iron. The Morosco meteorite uh, hit in Poland near Poznan. I think it was like, was it 5,000 years ago or 8,000 years ago? And I can't remember. Let's find out. So yeah, discovered in 1914. The Germans began digging it up, and it was found in what is now the Morosco Meteorite Nature Reserve. It is a park in Poland that you can go to. There are 7 meteor craters. I think 5 of them are filled with water, so it looks like a little pond. And yeah, it's really really neat. So let's go. Lunar Planetary Morosco. It is classified as that, and I don't have the impact date. When did it hit? Oh, okay, roughly about 5,000 years ago is when it hit. I thought between 5 and 8, but yeah. Um, so they tested the soil buried underneath the craters to about 3,500 to 5,000 years ago, and luminance dating when the soil was last exposed. It was about 5,000 years ago, so that's like the range that we say. Um, so it is a piece of iron, and again, it's pretty, it's neat, but it is just iron. You can buy pieces of it that are cut and polished, and they also have the same pattern as the one we saw before. Speaking of that same pattern, see what that looks like under the macro. We should look a lot neater. Oh yeah, and this one was not polished terribly well, but the pattern still comes out. You can still see it, and I'm going to try to use that purple light. See what that's going to look like. There we go. Oh, so you can see the crystals. They're either crossing each other and kind of hatched. So these striations, that's from cutting. That's what I meant by it wasn't polished terribly well. The striations that you see, those are from the saw, probably a diamond saw. Um, but the crystal patterns, those are inherent to the meteorite. See what the other side looks like. Maybe the other side is slightly better. No, it's the same. Again, you can see the crystals, the crystal pattern. It's almost like it's polarized, depending on how I'm moving it across. But it is fairly obvious as long as you polish it properly. Um, I guess while we're at it, we can look at 10331 again, just to see what it looks like close up. Let's see. Yep. So as we're looking at it, let's get the light on it again. Yeah, there we go. See all those shiny bits? Those shiny bits, that's nickel iron. And you can see it has a little bit of, I guess you call them striations too, on this big one here. Let's see, where is it? That one right there. You can see the little marks on it from the saw still. That's quite a bit of nickel iron all through here. Some of are little blobs. Some like right there. It's like a line almost, like a streak of it. Again, not sure why, but hey, it's there. This this purple light's a pretty good idea, isn't it? I should do this more often. I should take this out to outreach events. It'll really show up. But really neat how you can bring out some details that otherwise you wouldn't be able to see too easily. Because looking at this right now, the light's not bouncing off of it terribly well, but it's still fairly visible. I would have to do all this stuff, and there we go. You can see it like this, but then I gotta refocus it. Yeah. With that light, it just becomes much, much easier. Okay, take this one, put it by the side. If anyone has a request, if there's a meteorite that you heard about, maybe local in the area in Texas, you think, if you remember the name of it, you tell me where you think it was. If I have it, I can go dig it up. Maybe, if I have it. Big if. Um, ooh. So we've done chondrites. Um, we've done nickel iron. Now, stony iron. This one is a relatively famous one. This is a mesosiderite. Again, mesositerites, these are the ones that are, uh, they're a mix of stony and iron from a slow speed collision between a stony asteroid and an iron asteroid. And it's kind of all mixed in and jumbled together. And this one is from South America. This is from Chile. This one is called Vaca Muerte, dead cow, because apparently there's a geological feature called dead cow. Or there was a dead cow out in the middle of the desert and it was quite noticeable there and it didn't rot away and people used it as a landmark for all I know. Let's take the purple light. There we go. All the shiny bits. Shiny bits there, nickel iron. Shining in purple. That is pretty neat. It's got these veins in it too of the darker silicates. They're really showing up under this light. If I take this away, you can see it there too. Okay. Yeah, these are the dark veins. What's the other side look like? Ah, fusion crust. But if I do this, maybe, well, maybe it's a little bit shiny in places. This here looks like there's some protruding nickel iron right in this area. It's fairly bright. The purple light really isn't picking up very much. It's picked up a little bit over here. Get this right there. So if I do this, you can see a little bit of shininess right there. A little bit more shininess right over there too. Yeah. So purple. Neat trick. Okay. Vaca Muerte, the mesosiderite. This is a very, very famous mesosiderite. And again, if I take the magnet, because it's nickel iron, it sticks to it. Sticks to it rather well. Okay. And I always put these back right in the case because I don't want to mix any up. They're very, very small cases. So I want to keep everything together. Okay. Roscoe and Vaca Muerte. Ah, what else is interesting? Eucrites, diogenite. Okay, here we go. Now we talked about the head group, HED from the asteroid Vesta. We talked about the Howardites being crustal material. Here is a nice piece of Howardite. Bring it down a little bit so you can see the edge here. There we go. Okay. So this looks almost like concrete. And by that I mean it's a conglomeration of other materials. It's jagged bits like this here. This is jagged. All these pieces are jagged. They're not really. This one's kind of rounded, but not exactly um, jagged. This is a nice little jagged bit right there. It's broken up pieces that's cemented together, just like you would find for a lot of crustal material. It's not pristine. It's not one thing. It is a conglomeration of various materials. And all these spots over here, This large spot, these small spots all through here, this trail of spots, this is all rust. This meteorite is rusting. There's little bits of nickel iron. I can test this because it sticks. But if I do it over here, there's almost nothing. I don't feel anything over here. Maybe slightly over there. Yeah, I can feel a little bit over here. Kind of jumpy in this area. Oh, it got caught right there on this little piece. Wants to hang on to that. Yep, that's another piece right there. Wants to hang on to that. This piece grabs it very, very strongly. That little rust stain. And then we can check it again using the purple light. Where can we find nickel iron in this thing? Shiny bits right there, all the purple bits. Exactly where we thought. That is pretty cool. I'm pretty happy with this little trick. So these purple bits, that is the nickel iron, reflecting back purple light. So Howardites, crustal material from Vesta. This is actual surface rock from an asteroid. We know that this is an asteroid. Um, Back in 1999, we sent the Dawn probe to Vesta, and one of the reasons why is because we wanted to figure out what the surface was like. So orbiting it and taking spectrographic studies of the surface, basically looking at reflected light from the sun. So sunlight shines on the asteroid, reflects off of the asteroid. By analyzing the light in infrared frequencies coming off of the asteroid, we can match that to certain minerals that we have on Earth and that we have from asteroids. So the Howardites are named after a location in Australia where they were first found. We've had the samples for a while. We suspected they were from Vesta, we just didn't know until we sent Dawn. Dawn never landed, it just orbited Vesta and basically mapped out the surface um, with a mineral study so we know what minerals are on the surface. We compared those to the uh, meteorites that we have. So we are able to say, yes, this Howardite, this came from the asteroid 4 Vesta. This came from the crust of 4 Vesta. So again, free sample return mission from an asteroid. Just a random sample. We don't know exactly where it came from, which particular crater it came from, probably from the big one. But again, this is a rock from the asteroid Vesta. So this is crustal material. Let's go on. And now we're going to look at eucrite. This is Northwest Africa 12460. And this is something, is a tiny little sample, but this is a volcanic material from the asteroid Vesta. So from a volcano on an asteroid, this is a sample of rock. Just think about how unusual that is, that a volcano on a different body was hit by another asteroid, broke off pieces of it, and some of it eventually landed in the Earth or on the Earth in the Sahara. This one was found in 2018. Again, if you like, just type in NWA 12460 and you can go to the, let's see, which one is it? The Lunar and Planetary Institute, and you will find the meteorical bulletin database, and you can find information on this meteorite. And if anyone has pictures of it, you'll find the picture. So you can actually see, hey, does mine match up to what other people have for this meteorite? And this one does. We flip it over, see the other side, and it's pretty much the same. But again, volcanic rock. The reason why I have like samples like this is because some of these rocks can be very expensive. I cannot afford that. I just can't. And most people can't. So the meteorite dealers, they will often have a cutter who will be able to slice up a larger rock into much smaller pieces. So if I have this one, for example, I can have this one cut and then keep one piece and sell the other. And I asked my dealer about this a while ago, and I said, I like this big one. I don't really want to cut it. Um, just don't really want to cut it. And he goes, you know, I've never cut a meteorite and lost money. So while the smaller pieces won't sell as much as the whole big piece, you can sell a lot more of the smaller ones at a higher price overall and make more money selling these little pieces than you can with just selling one rock. Also, by having these smaller pieces, you can actually uh, you can have more people get access to a particular rock. More learning institutions can have access to it, have their own samples. More collectors can have their own samples. So it's not a bad thing that bigger rocks are cut into smaller rocks. So again, Northwest Africa, oops, 12460. Okay, so that one is a eucrite, so it's volcanic from 4 Vesta. Now we're going to go into Diogenes. Well, actually, no, here's another eucrite. Oh, I got two other eucrites here. Okay, cool. So this eucrite, 2015, Northwest Africa, 10364. And you can see this material looks different. Why does this look different? Well, different volcano, different geological processes, um, different magma for all we know. It just looks different. Cool. It's different, but it comes from the same object. It is still a eucrite. It is still volcanic in origin. And you can look this one up too, 10364. And you can find it. We'll flip it over, see what the other side looks like. Very similar. Again, small slice, but you get what the interior looks like. And then you can run it under the microscope. Speaking of which, see what it looks like under the microscope. Oh, I hope this works. Let's see. Yay. This is not the best of microscopes. This is probably the worst of microscopes. But this is a $20 electronic microscope, and it is not bad for what it is. So there we go. So I have a eucrite under a microscope. Oh, this is not the greatest of microscopes at all. No. But you can see some detail. And I may have to upgrade. Not a great image. We're able to see a little bit of the surface detail. It is some type of volcanic rock. That's all I got. All I got is it is a volcanic rock. So if we go back to big camera, we can see. So one eucrite, and I have another one which is actually much more interesting. Okay. So if I bring that one up, this is Tierhurt. This is one my dealer gave me. He thought it was super neat. Get a good focus on it. This looks like a little chunk of rock sugar. A little bit of white sugar, a little bit of brown sugar. But this is Tierhurt. Let me get this close. There we go. Tierhurt eucrite. Tirhert. Put it back. What happens if I rotate this thing around? Oops. How's that? That right there, the black, is fusion crust. And that black is melted material. It's actually quite a bit shiny. If I can get it on this side. Yep. It's quite a bit shiny. It looks a lot like burnt caramel when it's up close. It's the best way I describe it, but it is fusion crust and it's very, very thin. And this little bit is also some volcanic material. And it was blasted off of Vesta. I'm going to put this under the microscope because that actually has a fairly decent view. Well, maybe, maybe not. Not the best, but there we go. So you can see more of that black fusion crust. If I light up this side, yeah, it's really shiny. On that side, the fusion crust is quite shiny. The crystals there, they're shiny as well, but not as much. But that black fusion crust, and also you can see here on the microscope, it's a very, very thin. Fusion crust is only a couple microns thin. That's why the heat never gets to the inside. There's just not enough time for that to happen. So again, really neat. If I turn it over the other side, you can see more of the crystal formation. Again, it's Tierhurt. This is a eucrite volcanic rock from the asteroid for Vesta. Now, I just got to put this away. Here's a case again. Usually I just leave it sitting like this, and it's a neat little rock from a volcano on an asteroid. Um, one more. Oh, let's go deeper. Deeper on Vesta, and we're going to hit Northwest Africa 12793 diogenite found in 2019. Diogenites. What are diogenites? This is a deep mantle rock from the asteroid Vesta. Now, how many mantle rocks do we have from Earth? Really and truly none. None I can think of, at least. Um, Maybe, I don't know, would you consider, like, was it the kimberlite pipes where diamonds are found in South Africa? Is that really a mantle material? I'm not really sure. It could just be deep crust. But this is definitely a mantle material. I don't remember if this one is. Let's find out. NWA. This is 12793. I don't remember if this is deep or shallow. Ordinary chondrite, blah, 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 blah. No, this is ordinary chondrite. 3-9. I did 9-3. 3-9. There we go. Achondrite, diogenite, and this is not a deep diogenite, apparently. It's not olivine rich. Okay. Yep. But it has the very large crystals that you would typically see in a slowly cooling piece of magma from the mantle, or well, just mantle material, I guess. Let's see what happens if I shine the purple light on it. Let's see if anything is shiny. Now, no, not really. It's not shiny in the way other stuff was. So I see a tiny little shiny bit. Let's see what happens if I take the magnet to it. I'm going to guess because this is an achondrite and it's mantle material. Nope, I'm not feeling anything. Nothing is sticking. So if I found this out in the desert and I try to take the magnet to it and see, does it click? Does it stick? It does not. But then I'd be looking at fusion crust. I'd be looking, how does it feel? Um, and maybe I would have missed it. And that's the thing. If all you're doing is using a magnet to determine is it a meteorite or not, you may miss a lot. Maybe not a lot, but you'll miss the interesting ones. So again, this is material from deep in the mantle of an asteroid. And that's not something that we really have of anything else. I mean, we can't really dig down deep into our mantle and get anything. Can't do it for Mars. Can't do it for Venus. We really can't do it to any asteroid. Uh, we can't dig down into Ceres into its mantle either. It's a couple hundred kilometers down. So stuff like this is all we can do. Now we can do some cool stuff like this. This is Northwest Africa. If I can get this thing off. Northwest Africa. Lost my label. It fell. One moment. Okay, Northwest Africa. 12965. This one is Martian. This is a Mars Shergotite. So we had found some Shergotites before, and we suspected they were Martian. But it wasn't really until we sent rovers to Mars that could start analyzing rocks did we know for certain, yes, Shergotites are Martian rocks. And so sometime in the distant past, something hit Mars, made a crater, blasted out pieces. They went around and around the solar system, no telling how long, and eventually this one landed in Northwest Africa, out in the Sahara Desert. Somebody found it and thought, hey, this looks neat, and went and had it analyzed. And let's see what happens. Nothing. Nothing at all. I'm not feeling anything here. So, no iron, no nickel iron, does not react to the magnet, and yet it is a meteorite. It's a Martian Shergotite. So really, really neat. A piece of Mars in my hand. Not everybody can say that. This is one that I don't let people touch because it's a Mars rock. I mean, it's really cool. I let people hold it in the case like this. I don't let them hold the rock itself because it is so small. It is so delicate. But there is one I do let people hold. This guy. Who's this guy? This is Northwest Africa 11421. This is a lunar feldspathic breccia. So it is a conglomerate of a bunch of different rocks. Is it magnetic? There is that one rust spot at the top. Let's see if it picks it up. Not really. It may not be rust either, just maybe red from another mineral. Um, Moon rocks typically do not have any or very, very little nickel iron in them. Um, they have aluminum ox. I don't remember. Is aluminum compounds? I don't remember. I don't think they're aluminum oxides, but I don't remember off the top of my head. But there is aluminum on the moon. But this is a little moon rock, and this one I do let people hold during outreach events. It's small enough that it fits in the palm of their hand. I mean, if I put my finger right next to it, you can see it's a little bigger than my fingernail. Um, but it is a piece of the moon. And what I usually like to do is, especially if they're little kids, I take it out. I don't tell them what it is, and I put it in the palm of their hand. Have their parents pull out their cell phones, take some pictures, and I say, "This is a rock from the moon." And kids' faces usually light up; they get really happy, and that's the best time to take a picture. So, forming core memories. That's something that we have to try to do as science communicators. So, this little rock we know came from the moon. This landed in Northwest Africa near Tindouf and Algeria, and the discoverers, the Polish meteorite hunters, they were suspicious that it was a moon rock, sent it off for analysis, and it came back as, yes, this is lunar material. And we know that because the Apollo astronauts brought back rocks from the moon, and we're able to analyze those. We know the composition, we know what they look like, and we're able to compare other lunar rocks to the stuff that they brought back, both highland silicates and basaltic rocks from the Maria. And we were able to say, yes, these meteorites are lunar material. So NASA doesn't have all the moon rocks uh, in the world. They just have the ones that they brought back themselves on Apollo. There are a lot of moon rocks, and a lot of us collectors have at least one or two samples of them. So this is my sample, and it's a really neat one. And this is the one that I let people touch and hold because it's not every day that you go out to an event like a star party and someone says, "Hey, you want to hold a moon rock?" So that's always really neat. Here's another sample of the same one, exact same rock, except this one is an end piece. So here, this one didn't really have a fusion crust. Um, Not sure why. I've never gotten a straight answer on why this one does not have a fusion crust, but it does not. It's 914 grams for the entire object. Um, Not very big. Broken up into a lot of pieces. It broke fairly easily, apparently, um, relatively, I should say. Uh, but yeah, this one did not really have any noticeable fusion crust. Again, not sure why. It's not terribly common with meteorites, but I guess it does happen. You can see some of the material here on the outside. And again, Northwest Africa 11421, if you want to look it up. There's just there's no um, there's no nickel iron there to be shiny. It's just that piece, but the rough end piece. But we have the polished side. Polished side, if I can get it here, focusing good. You know what? I'm gonna move this down. There we go. And focus. So when we're looking at this one, we can see the clasts. So the clasts are these white pieces. They're larger rocks, well, relatively large. Some are fairly small, but they're larger pieces of rocks, of silicates, and they're held together in this darker matrix. So it is a conglomerate. It's pieces all stuck together, but they are stuck together pretty well. So I mean, I could break this thing with my hand, but I'm not going to. Um, it's got cracks in it already, so these cracks through here, I don't want to mess them up. So I'm very delicate with it, and I tend to keep it in just a case, and not. I take it with me, but I don't hand it out for people to touch, just because of how delicate it is. We also talked about carbonaceous chondrites. And again, if you have any questions, comments, let me know, and I'll just put them in the chat, and I will answer them. Um, Carbonaceous chondrites. These are chondrites that formed further out from the asteroid belt, where the temperature was lower, where they were able to condense out uh, from the uh, from the protoplanetary disk. Yes, I'm smelling it. I haven't smelled it for a while. I have to smell it right away. This Aquasarchus. Aquasarchus is a carbonaceous chondrite that landed in Costa Rica in 2019. The reason why I was smelling it is because it has carbonaceous chondrites, when they're fresh, they have a really distinct smell. We call it the smell of space. It's burnt, but it's not burnt like anything else you've ever smelled. It's kind of like burned metal, but not exactly. It's kind of like burnt stone, but again, not exactly. And if you've never smelled burnt stone, then it's not exactly volcanic. It's it's kind of That's the thing. It's the smell of space. It's the best way I can describe it. It's very, very unique burnt smell. Um, this does not have. Oh yeah, it does. It has a little bit of iron in it. Not very much though. Just tiny little bits. Oh great! Now I'm gonna have to get it off. But it's a very, very small sample that I have, and when it was really fresh, it had a very noticeable smell to it. Yeah, these little bitty tiny flecks that you see, little bright spots. I think that's the nickel iron. And again, very, very unique. And some people can smell it very easily. Some people just don't smell anything. But I keep it in the case and I only open up every once in a while so the smell concentrates, and I can get that. And it's a burnt smell. Best way I can think to describe it. It's a unique burnt smell. We just call it the smell of space. And it's from the organic compounds outgassing from it. All right. So Aquazarcus, Costa Rica. And Costa Rica. Costa Rica has forests, doesn't it? Yeah. But this was an observed fall. Um, People saw this come down and then people went hunting for it. So it wasn't a situation where it was, oh, I just stumbled upon it in the forest. No, no, no. Okay. Northwest Africa, 8327. Do it this side first. It's got a very lovely fusion crust. It's very, very obvious. Uh, it's dark. It's a little bit of crackle to it. Um, but it is definitely fusion crust. Got some chips on it. There's a chip right there, another chip right there. But that's fine. However, this is one of my favorites because when I turn it over, it's like this. It sounds like terrazzo. These are chondrules, little round bits. A little bit right there, a little dark one. That's a chondrule. All those rust spots, nickel iron. Round chondrule, 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 chondrule. All these little bits are large chondrules. Again, we use purple light. All the shiny bits. Nickel iron. I'm sorry, that's just really cool that I can do something like this. All those little shiny bits. Purple shinies is nickel iron. Little flecks of nickel iron. But the chondrules themselves, I'm going to take this under the microscope because it just makes it really obvious. One microscope. There we go. You can see these round little chondrules all through here. The shiny bits, metal, nickel iron, some white bits. If I can get a tiny bit better. Nope, that's a tiny bit worse. There we go. That's pretty good. Okay, look at the edge. Just look at the edge. Um, do I have something I can put underneath there? This is doable right there. Okay, I'm gonna use this instead. One, two, there we go. That's the fusion crust edge. It is just a few microns thick, and it's cutting some of these chondrules in half. But the inside of the chondrule, it's not affected at all. It's only that very, very thin fusion crust on the outside, just microns thick, even on such a small piece. The heat never had time to get down into the center, even on a little pebble like this. All the heat was taken away, it was ablated away with the other material on the outside. All that heat went away. Nothing went inside. And so these chondrules are just cut in half. Fusion crust on the one side, unaffected on the interior. So we can't really replicate that on Earth. You can't get a blowtorch hot enough that it would ablate away the material um, at the same time that it doesn't affect the inside. We just can't. I had a coworker one time who, when I showed him this, he said, "Oh well, I'm going to sell you a bunch of meteorites that I have in my backyard. I'll just take a blowtorch to them and make them black just like this." It's not the same. It's just not the same. We can very easily tell if it's a real fusion crust or if someone's trying to fake just by doing this. By cutting it open, putting it under a microscope, we can see the insides, we can see the chondrules, we can see the minerals, we can see the nickel iron, we can test all this stuff, and we can tell, is this a meteorite? Is this not a meteorite? This is definitely a meteorite. Um, I like to show this one off a lot just because I think it's just really, really pretty. And when I put it back under the macro, so I've had people tell me that's really pretty. It looks like terrazzo, like like the Italian concrete flooring, and it's really pretty. And I've had someone say, I'd love to make a bar top out of this. It'd be gorgeous instead of like granite to use something like this. Yeah, it would be. The problem is this is $4, $5, $6 a gram, if not a little bit more, for named stones. Um, so this will be the most expensive countertop in the world. If you can find enough of this material, and you just can't. You would have to go to the actual asteroid and start mining it. But again, very pretty. Looks like terrazzo and nickel iron. So you can pick it up. Yep, it's sticking. Over here. Yep, yep, it's sticking. So a little bit of nickel iron, not very much, but it's enough that it does stick. We are nearly done. Got a couple more here, sugatites. Uh, we did a mesosite. It's time for a palisite. This one is, oh, this is the danger. I haven't opened up this one. This is Simchin. This is a palisite. And it is rusting away. It is dying. See, there's a lot of rust. It's falling apart. There are bits and pieces that are still shiny down here, but it's coming apart. You see the crystals of olivine. It's just not it's just not pretty anymore. But if I take this, now you can see the metal. Now you can see the nickel iron just shining, really bright, and the olivine crystals in between. And those scratches, that's just from probably from polishing process. Um, they're not Widmanstatten patterns, Widmanstatten, but all that, yep, all the dark stuff that is nickel iron, and the other stuff is olivine crystals. When they're in really good shape, they're very, very pretty. You just have to take care of them. I didn't realize this one was rusting away and falling apart, but it is. And it's got little, yeah, olivine crystals that are breaking off from the larger mass. But here we go. You can look this one up. Semchan, Samenchan, Samechan. It's a palisite. 9 grams. But man, is it just coming apart. Ah. So I keep this one boxed up. And if it falls apart completely, fine. It falls apart completely. I'll eventually get another one. Something nicer. But in the meantime, I still have that one. Morosco, we already did the Morosco. Um, ah, where's my case? There it is. Okay. So we've seen meteorites. Let's look at some meteorongs. I do this with kids. When I do outreach, I'll have a bunch of these out as well, and some magnets. I'll say which ones are meteorites, which ones are not, and get them to actually look at it, hold it, touch it, mess with the magnets, figure out what is a real space rock and what's not. So, oh, 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 yes. I guess we can take off this lens. We can go back to the wide angle. Uh, so I have rocks that I put in. This one, piece of nice. It's nice, and it is smooth, very smooth. It's a river walk, river rock. I think I picked this up in Colorado. I was I was 12, well, 11, 13, somewhere about there. Um, and I've just had it ever since. But it's a neat rock. It's pretty. But this is not a space rock. It is heavy. It feels heavy, but compared to a rock of roughly equal size, it's lighter. This one's heavier. So I have this one out, and it's one of those where, yep, this is a meteor wrong. So kids, you know, kids can see. Hey, here's one that's smooth. It's white. What is it? Limestone from the garden. Um, but it's smooth. It's smooth just like a meteorite is smooth. Okay, it's not as shiny. But again, it's showing differences and letting kids feel. Yeah, this one's denser than this one. This one's feels heavier for the same size. Gee, this one's yeah, not exactly close, but that's okay. Um, this one's very smooth, but this is some type of a siltstone with a calcite intrusion. And again, it's not a meteorite, but it and magnets don't stick to it. I'll have a stronger magnet. Magnets don't stick to any of these, but it's something for kids to be able to play with to see. And then I have this guy. This guy is probably rarer than most meteorites. It's probably very rare. Hard to see. I'm going to put it under the microscope. It's dense. It's very hard, but it's still not nearly as dense as a meteorite of the same size. But this guy here, oops, this is a rock called lanite, found near Llano, Texas. It is a pink granite with blue or purple uh, quartz crystals in it. Let's see, there we go. See the quartz crystals on the side. When it's polished, it is a very pretty rock. And now that I think about it, I think I know exactly where I left one. Uh, but I'm not gonna get it. It looks dark when you polish it nicely. Um, the crystals are blue or purple. It's just a very pretty rock. You find this in one place in Texas, near Llano, Texas. You go north on Highway 6 from Llano, and you go to the map and you find it where Baby Head Cemetery is. Don't ask, I don't know why. But just past Baby Head on Highway 6, you go up this little hill, and there's a rock outcropping on either side of the highway. This is a volcanic dike. And this is the only place in Texas, well, anywhere, where there's a with public access to get to that rock. And uh, people go out there with sledgehammers to try to break off pieces to take home and to polish because it's such a unique rock that you just can't find anywhere else. So um, these are meteorongs. They're interesting rocks. They're all different, but they are not meteorites. And it's really obvious when you put a meteorite right next to them. So I'm going to do this. I'm going to swap it out for the other lens again because um, I have other meteorites that I can do. But the question is, got so many, and it's like it's just repeating the different types that I already have. So each is unique, each tells its own story, but necessarily it might not be necessary to see every single one of them. Be here all night, and it's already 11 o'clock. It's after 11, and I have work tomorrow. So let's do this. I'm going to swap this out, and then we'll finish up with one more rock. This other rock is going to be our case study. Why? Well, you'll find out in a bit. So we talked about it before. Trying to be very careful. Cover everything up. All right, we're going to go back to the wide angle. Okay. All right, so switching to, there we go. So now we can see, we can see one meteorite next to a bunch of meteorons. Real meteorite versus Earth rocks. I don't want to say fake meteorite because they're not fake. They're rocks. They're just misidentified. If someone happened to be misidentifying them as a meteorite, they are not meteorites. They are just Earth rocks. Now, pushing those out of the way. Here's our case study. This guy. So first, let's do this. Big rock. It's heavy. It's 8 kilos. So it's significantly heavier than an Earth rock, a normal rock you would find of this size. Yeah, magnet sticks to it pretty well. The magnet, oh yeah, see, that's really sticky. Oh, sticks. Okay, it's dark. It's a dark rock. It looks weird, and it's heavy and a magnet sticks. Could this be a meteorite? Well, put it underneath camera. Well, oh, let's fix this. There we go. Well, what do you think? Is this a meteorite? Is this not a meteorite? It's dark, kind of has a fusion crust. Or it looks what it's dark like a fusion crust. It's weird. It's got these weird pock marks all over it. It's heavy. Again, magnet sticks to it. Magnet sticks to it really well. Just wherever. Um, is this a meteorite? No, this is not a meteorite. This is in fact a piece of um, Chinese slag, or well, it's a piece of Chinese steel. It looks like it fell off of a large crucible and was thrown away and dumped into a river. Look at this side. That looks weird. That's just not expected. So, this is not a meteorite. And the way you test it, just to make absolutely sure, is you do a nickel test on it, and there's almost no nickel in this. So, not a meteorite. I pretty much knew it as soon as it was in my hand. Where did I get this thing? I got this from eBay, from a seller many years ago. who said that he found it in a river and thought it was a meteorite. Looked at it, it's like kind of suspicious, um, but it's not terribly expensive. I'll get it. If it's a meteorite, yay, lots of money. If not, I didn't lose much. But as soon as I got it in my hand, it was just obvious it wasn't. Testing it revealed it's definitely not a meteorite. It's Earth steel, iron of some type. Um, and so I emailed them back and said, "Hey, this just is not a meteorite. You can't be selling these as meteorites." And he emailed me back and said, "If I give you half your money back, will that be okay?" I said, "No, it's not a meteorite." Um, and a couple weeks later, I found that eBay had refunded all my money. So, oh, okay. But I'm not going to send back 8 kilos of trash steel back to China. So, uh, this is an object lesson in why you have to be careful in who you buy meteorites from. You don't buy them from random people on eBay. There are some dealers that I do use that have in the past, and they are very good. They are knowledgeable. Um, they're just really good dealers. Uh, you can always email the club, and I can give you a list if you'd like. You can look online. Galactic Stone is a good one. They sell on eBay, and they have their own web front or storefront. Uh, WW Meteorites is a very good one. Um, he is up in the Shetland Islands, and he is the one who does these little bitty pieces. He's very good. And of course, there's polandmet.com. Polandmet.com. Put this down like this. Push that out of the way. Polandmet.com. And again, I'm not getting paid any royalties or anything from these guys. It's just I've used them before. They're absolutely trustworthy. Uh, they have very very good reputation. So um, yeah, if you're looking for something, that's the way to go. You go with a trusted known dealer. You don't go from random guy on eBay because you never know what you're going to get. And I mean, yeah, you do. You're going to get a piece of Chinese steel like this, or you're going to get something. You may actually get a real meteorite, but there's just no telling. Um, so, any other questions, comments, concerns? Uh, if not, then there's about a 30-second delay on the stream. So if you have any questions, yeah, just go ahead and put them in. I'll answer them best I can. If there's anything that you can think of that is meteorite related, or if you can think of a specific meteorite that I might have, let me know. Um, give you a couple more, give you another minute or so, and while I go over this. Oh, we did miss one. I guess. Let's see. Fredericksburg. Yeah. I guess the other camera, the other lens would have been better for this one. I guess I forgot. Oh well, that's fine. Fredericksburg. This one is one from Texas. This is a nickel iron. It's very small. It's not very big at all. Look the other way. Let's see if I can focus. There we go. And with the purple light, it's all nice and shiny. The whole thing is fairly shiny. Um, I picked up a bunch of Texas meteorites. I had an opportunity to because, well, this is Texas. I was looking for several. I did find one for Forestburg. Forestburg is located north of Decatur. So, for those not in the Dallas Fort Worth area, you go north of Fort Worth, and then you go northwest of Fort Worth to a town called Decatur. And from Decatur, you go north. After a bit, you get to the Forestburg area. And the reason why I got that one is because at that time, we had a dark sky site that we were um, renting for, I believe, $1 a year at a private nature reserve. And we had concrete pads and we had powers, very, very nice place. Um, but they closed it off during COVID and never reopened it to the public. So we had to leave. And I thought, well, Fredericksburg, meteorite that landed near our dark sky site. That'd be pretty cool. And then we left that dark sky site. So, oh well. We have Fredericksburg. I have Eater. I have a couple of others as well. But it is getting late. It is now 11:30 at night. I've been going on for 3.5 hours. I think that's enough. I don't see any questions online right now. So if everyone's pretty happy, I'm pretty happy. Um, Again, it's late. Hopefully, you'll be able to do some more of these. I do have plans on doing some live streams for virtual star parties again. The studio is all set up nicely, so I can go ahead and do those. The only issue is that we've had very poor weather this year. In the spring, we had rain and clouds quite a bit. And then now we have heat. We also have high winds. So I thought about actually taking a telescope out tonight and doing a remote session to the telescope, showing off some asteroids for International Asteroid Day. Unfortunately, we have 10 to 20-mile-an-hour winds, and the telescope that I was going to use is not in a building. It is out in the open, and it will shake like mad, and we will see nothing. So, was not any point in doing this. Hopefully, soon we'll be able to do something. If the weather is good, I may be able to do a star party from our new dark sky site, about 2 hours west of Fort Worth, um, south of Cisco and Ranger. It is in a very nice dark sky site. We have Bortle 2 skies, and we actually have a dome there right now with a telescope. Hopefully, soon I will be able to connect directly to that telescope and do live star parties from there. So we'll be able to see the night sky from a dark sky site while I sit comfortably at home with air conditioning and drinks.